hear me? 1, 2, 3, 1, 2, 3, probant. Més amunt, més amunt. Hello. Good morning, everyone. Okay, can you hear me? Yeah, guess so. So, yeah, it works anyway. Good morning. Can you hear me? Yes. Cool. So welcome everyone to the r2con 2024. So this is the keynote. It's not any presentation. I will just talk a little bit about the conference. It's been 5 years since the last r2con, so it's been a really long time. There was a lot of people asking for the conference to come back. Yeah, finally, we are back. I don't know if you thought about the logo. I mean, the conference has a different logo every year, and there is like a story behind that. It's a phoenix bird, and well, the reason is because it's kind of like reborning, like trying to begin again from start. And yeah, I mean, there was COVID in the middle, there was a community split, there was personal dramas. Yeah, the development was slowing down. But yeah, I try to keep pushing commits every day, trying to think in a better way to organize the project and also the code and also the community. And yeah, I learned a lot of lessons in the process. And yeah, and during this time, I was trying to find the mood, trying to get all the confidence to get everything reassembled again. Seems like at the end, a bunch of people was also helping on the organization, and we finally make it. So we're trying to have like a very humble objective this time. The idea is to just have the conference. We don't want to make special things like the R2 Wars competition, the concert on chiptune at the end. There was the CTF, we are not also organizing it. And we're trying to make like simple conference, 2 days, trainings, presentations, and not trying to make any extra stuff. But yeah, we're trying to make some baby steps to move forward because we have like a long way to go. We have cheat sheets and beers. There is coffee. There was like speakers dinner the first night. Yeah, at the end we have the most important thing, which is basically you. So thanks all of you for coming and attending the conference, because without you, probably it doesn't make sense to organize this thing. And I'm so happy that we can have fun together and have some presentations and share all the stuff that we are doing. We'd like to talk a little bit about the project. From the code point of view, there was a lot of changes during this time. Mainly it was focusing on simplifying the maintenance of the code and simplifying as much as possible all the development process. I was trying to keep pushing new changes and trying to make the tech debt as simple as possible, because this way I was simplifying a lot the release process, the CI, all the code maintenance, trying to reduce the amount of people that was involved into the project, not because we want to have less people, but because the less needs for people simplifies and reduce a lot of the stress on the project and also all the dependencies. So one of the things that I decided was to make like a ABI stable since 5.6. And this is an important change, because having like a ABI stable means that you can rebuild R2 or change any of the plugins without having to break everything. So you don't need to rebuild everything all the time, which is, from the user point of view, is interesting. But if you're a company, or you have some tools, or you have some products, or you have different things that are relying on R2, you don't have to change the APIs. You don't have to rebuild everything all the time. You just have like one build that works, it's stable, and then you can replace this build with different version and find out which is the regression point much quicker. Also, there was like a friend that was packaging it for Flatpak. So Plu, with Pau Rodriguez, was packaging it for Flatpak, which is also simplifying a lot the process for deploying new builds for Linux and also for Windows subsystem. And also we have new Debian packagers and maintainers, which is also helping a lot for many users that don't want to depend on building R2 from the CI, from Git. Also, there was a lot of performance improvements since the last release. There is, like, for example, I think that there is like 2 or 3 times faster analysis in the last year. So there was a lot of performance improvements in binary parsing, also code analysis, mainly focused on stability. So we keep having the full disclosure security rule, which means that if there is any bug or any issue that affects the security in the tool, we make that public for everyone, and we fix that in less than a day. I think that this is probably the sanest way for publishing vulnerabilities, at least because we are like an open source project, and we want to force people to contribute and make everything as open as possible. And we want to make all that possible without reducing the amount of possibilities or functionality and features that the tool is providing. Also, during this last year, I've been working on the book. So there is a book outside. You can take it. And it's not the last version. You can read and use all the comments that are there, because actually most of the comments and the APIs that were described in the book are still stable and still usable. But there is so many other things, and there is a lot of rewarding and better ways to explain all the features that the tool is providing. And you can basically find out the new or revamped version of the book online. And we probably end up like printing a new version in next year. There is new tools, there is new features, plugins. During this last year, there was like R2 AI. There was like the big boom on language models, and everyone is talking about that. There will be some presentations on this. Yeah, there is, for example, the r2 Clippy, which is the joke that we had at the beginning of the project, that Clippy was helping on reverse engineering some binaries, but finally we can make it happen. So actually there is r2 Clippy, which is an ASCII art assistant that is helping you on automating some process on reverse engineering. It's also possible to explain what the function is doing, helping on the compilation, doing type propagation, function analysis, and many other stuff like vulnerability finding and so on. Also, r2 Frida was written in TypeScript. This was a major change because the whole code base was written in JavaScript in the past, and having types help us to improve the code quality and the maintenance quite a lot. The last version of Frida is introducing white points and breakpoints. This means that we can soon end up having Frida as a native debugger backend. So you will need to depend on ptrace or match APIs for debugging. We can also use Frida as an 100% stable and reliable debugger that works with a simple API. The R2 Yara plugin was rewritten. It's also having like a test suite. There is new features. There's comments for creating Yara rules and creating function signatures in a better way. And the compiler status has changed quite a bit. So now we have 3 new decompilers. There is Anger decompiler, which is quite stable and reliable. It's quite slow, but as long as R2 have the compiler output catch, now you can basically spend a while getting the output from Anger decompilation, and then you can just analyze and see all the analysis on the compilation for all the binary without having to wait for the decompiler to respond. Also the Kai, which is the R2 AI decompiler. RepNG, which was open sourced, I think it was last year. And also PDC, which is the pseudo decompiler that is shipped in R2, has been improved quite a lot, mainly because this is what RDKI is using behind the scenes. The JADEX decompiler finally made a new release fixing one of the major issues that we had in the JSON output. So this is also updated, and we can use JADEX again inside R2. R2 Git and R2 Deck are still maintained. They're still there, but they're like not improving as much as all the other compilers. And finally, RedDeck seems to be abandoned. I mean, nobody's maintaining the plugin. So if anybody wants to contribute on that or in any other compilers, everyone's welcome on this. We try to keep the spirit. R2 is an open source project. We want to have a free tool for reverse engineering. We want to have no ties with anyone. We just want to have the project as open as possible. We want to have like an open discussion platform, so everyone is open to contribute, discuss things, explain whatever issues they have, not just in the code base, but also in the community management, in the way that we organize the event. We will be sending you a document that you can, at the end of the conference, that you can respond by mail and give us some feedback anonymously. So we'll just want to improve, and we want to have everybody as comfortable as possible. As long as the project is open, we don't have like a strict development process. So the development decisions and the roadmap are defined by you. So if you need anything, if the company you're working on, your friends are reverse engineering any specific project, and there is something that is not working as well as it should, or not supporting a specific architecture, just contribute or fill tickets and ask us for support, or if you need anything, just push the changes, and we will be so happy to have this stuff working. And yeah, as always, we want everybody to use r2con Git. Right now, it's pretty stable, so you can just download the last release from day2 or r2 and use it from there. But we try to have everybody using it from Git, because we push changes every day, and there is a lot of bugs that get fixed as soon as possible. Also, to finish the presentation, I would like to thank the university for having us. So also, I would like to thank Grey Hat, which is the organization from the hacking club that is here in the university, helping us in the organization of the event. It was impossible to find a better place to organize the event, so thanks again, Grey Hat and UPC, for having us. Finally, Radare is an organization. It's a non-profit organization, so this means that we can organize all the economical stuff and looking for places in a better way, so it's not just depending on a personal situation. Also, I would like to thank many people. I mean, just mentioning few here, but I would like to thank Conrad for the long chat that we had and discussing not just technical things, but also from the conference and the organization for the project. I would like to thank NowSecure, which is the company I'm working on, for supporting me, supporting the project, and helping also on the conference. I would like to thank IPK Unpacker, which is one of the main Termax maintainers and testers, and also fixing and reporting many things on the Android reverse engineering side. I would like to thank Hossein for all the music that we were listening during the conference. He basically contributed to the conference with a playlist that is public and copyleft. Also, I would like to thank Malware Must Die and all the community from Japan, because they are keeping the community and the event happening in the other side of the wall. And also thanks to everybody for attending, and hope you have like a good conference and enjoy the event. So thanks everyone, and we'll start soon.
Hello. Good morning. So we are going to start the next talk. The first one is done by Ula. I'm just the creator of Frida. You know it. And he's going to present some new features that are applied to Frida. And just a round of applause for him.
show you some improvements to frida-trace, which is part of package called frida-tools. You get it through pip install frida-tools typically. There's now a new R2 integration there. Before we get into that, I want to show you just how this tool was typically used in the past. And that was what motivated these new features. So before we do that, we're just going to write a small test program. The idea is that we're going to have a really simple program so we can understand what we're actually looking at. So we're just going to have an infinite loop. We're going to call a function f, and we're going to give it an integer on each call, and it starts at 1. And we're going to delay 1 second between each call. I'm going to need uni_stdh for sleep, and standard bool for the true constant down there. And we're going to define the function f that we're going to call. So it's given a number n, so it's just going to print that number. And we're also going to print out where f is in memory. You'll see soon why that is useful, but we'll start there. So yeah. So we're going to just run this program, and you can see that the function f is getting called. Yeah, that's it. So now we're going to actually use frida-trace. So we'll do frida-trace hello, which is the name of the process. We could also use a PID, process ID. We're going to do like, we know that printf is getting called, so we can include that. And we know that sleep is getting called, so we'll include that. So we're going to trace those two functions. I'm going to run that inside the demo directory, so it's easier to see what this does, because it's going to produce some files on the file system. So here you can see that we're tracing these two functions. What also happens is that there's a handlers directory generated on the file system, and there's a subdirectory per library that we found functions in that we're going to trace. So here there's libsystem c dilib, and there's like printf and sleep.js, so one generated per function. So now we could go here, and actually this will just generate a boilerplate for us, so we can start like changing the logging or logging what we want. So here you might want to say just change this, for example, to add r2con, and if I save this, it auto reloads, live reloads this hook, so you can see the new output now. So that is useful as a feedback loop for reversing. So here we could also trace the function f. So we could, but then we'd have to start this program over to like add -i, and that's kind of not a great workflow. So that was what motivated this new UI that I'm going to show you. You can also spawn a program like this, oops, -f, and then the path to the binary, and like sleep, printf. So that's another way. But and then if you trace something that's called very early, then you have to run it again. So Control-C arrow. I mean, it's repetitive. That's another part of it that gets boring quick. Yeah, basically these are the reasons that I decided that we need a UI for this. So if we go back now to the example we have with tracing The hello process, we're including these two functions. With the new version of Frida tools, frida-trace will actually tell you, started tracing two functions, web UI available at localhost on this port. So you can open that up, and that is the new web UI. So you can see that they're in sync. And now here, if you actually, I should probably make this a bit larger. So here, if you now click on one of these events here in the log output, you'll see it will actually open the editor here to take you to the code. And here we're using the Monaco editor that VS Code uses, so that means we have code completion. And that means you have inline docs of the whole Frida API, and you'll have type checking and code completion. So that is handy. You can also hover over a variable to see that it has this type. So yeah, now we can, for example, let's close this. Change this hello there and hit deploy, or I can do Command S or Control S depending on the OS. And now I can click this latest event button to go straight to the latest instead of scrolling down the view on the bottom. So this will take me to the latest event from this particular handler that we're editing here. Yeah, and then if we think that this one gets a bit noisy, we can hit the mute button here. And now it's red in the left side here. And we only see sleep now, output from sleep. And you can go and mute that too, and there's going to be no output. And unmute, and yeah, it's going to be back. So, so that means you could do like, say you want to do, typically in like before the UI, you would want to like know, okay, sleep is called, but where is it called from? Okay, called from, and then insert a backtrace. And then you'll define a backtrace as thread, backtrace this context. Backtrace gives you an array of native pointers, so you can map that to debug symbol from address, and you can join those by new line and tab, and save, and you'll see here that, yeah, you get the call stack. This is tedious to do, so now with this UI, we don't actually have to do this at all. Just remove this, go back to where we were, and I'm going to just toggle capture backtraces here. So now if you look at an old event, you'll see just the caller, but if you go to the latest, you'll see that there's a backtrace. So now we've enabled backtraces just for this function. So you're only paying the performance overhead of it for this particular hook. And now let's look at the R2 integration. So these enters in the backtrace, if you click one of them, it will take you to, we'll use R2. And this is running entirely in the browser. You don't need R2 on your system even. So this means that we're turning Frida users into R2 users overnight just by deploying this new version. And here in this view, like if you have a branch target like here, it becomes a link, so you can click on it to go there. And this integrates with a browser's navigation state, so you can do back here, like you go back to where you were, or forward again. And then say here on this particular instruction, I want to have a hook just here. You can click and do add instruction level hook, and click that, and now we're tracing that too. And it takes, the editor opens here with a handler. That looks a bit different from the other one. If you look here, it has on enter on leave with an object. An instruction level hook has just a function. And now, hopefully, we'll have, yeah, go to the latest event. Yeah, here we go. So whenever this function, instruction is hit, this code here is run, and you can do whatever you want. So here, You could do log x0 if you want instead, for example. Go to the latest event. Oh, yeah, and latest event. And it didn't update. Demo effect. It doesn't use, so this is plain JavaScript, but the editor thinks it's TypeScript, so it's a bit confusing. That should be improved. Testing, deploy. Yeah. Oh, SP, I forgot to up. Okay, I need coffee. Let's try. Yeah. So this is x0. Yeah. So you get the idea. Now, if you're looking at this disassembly view and say you have a memory address here, we have an adder p x16 and so on with an address. You can choose between disassembling and viewing the memory. So you can do view memory, and here you have the R2 powered memory viewer, and you can go up and down in memory here or type an address. You can change it to different views, or periscope view, for example. And it integrates with the navigation state as well, so you can go back to where you were. And if you were to spawn the process like here, then you'll also see the respawn button. So that means you can just hit this, and you should see that it's respawning the program. And so this means if you have if you're hooking something that's called very early only, then you'll just hit this button instead of the longer restart loop that you had before. Okay, so yeah, going back to the attached state we have here. Oh yeah, and it has a different port number on this run, of course. So another thing you can do, which is actually where the whole thing, where this thing started, is I want to add more stuff to trace. So should have started with that actually, but yeah, that's the add UI for that now. And here you can. The UI is not awesome, but yeah, here we go. So you can choose what kind of function you want to add. This would be like, function here would be like -i, and relative function would be -a, and so on. So like if you switch this one, it will tell you the syntax, like module ! offset. So if you want to hook something where you don't have a symbol to look it up and export or something, then you can do it relative to a module, but you can also do an absolute address. So that comes handy here when you have the function f, you know where it is in memory. So you can just copy that address and plop it in here and do, add this. Hopefully, yeah, hello, inson 3f3c. So we know that this is f, so we can do f hit. And go to the latest event. Yeah, here we go. And here we know that the first argument is the n, the integer that's passed to it. So we can do n equals save and go to the latest event. Yeah, to see the number now. And if we scroll this to the very bottom, you'll see that they're in sync with the terminal output from the hello world program and the event output here. So now we have a live trace of this. On this. And now we can quickly switch between, like, click on events here to go to the handler of each. So if we don't like the output, I can quickly go to the code and change what we're logging. as you're learning more and more about the target. So say here, you can add Swift stuff, or you can do like module function, so you can do like open star, for example. And yeah, this will give you feedback as you're typing, and you can choose to add all of them that matched, or just one of them, for example. Yeah, open PTY, for example. And here it is. So now I think we could take a quick look behind the scenes of how this works, since we still have some time. So that is that is a component called React use R2. Or actually, let's start with the UI. Oops. So yeah, in the Frida tools repo, there's an apps subdirectory which has a tracer subdirectory, and that is a single page app that's running in the browser. And for example, the memory view, to take that as an example, it imports use R2 from Frida at frida/react use R2. And this gives us an execute R2 command. And then now here we're using the UI toolkit called React. We're setting up basically a side effect here that's going to happen whenever one of these things change. We're going to execute an R2 command, and that's going to be rendered in the UI, the result of that, or the state that it updates. And you can see, like, yeah, this is the HTML that we generate here in the browser. So down here, you can, yeah, we have a div where we have the memory view data, where we output the, where we show the R2 output. And then we use dangerously set inner HTML with the HTML that we got from R2, because we're setting up for HTML output. So it renders, instead of ANSI escape codes, it will have HTML tags. And then we have a bunch of, we have the segment and control to select like what kind of memory view you want, like raw, 64, 32, periscope, and this runs this R2 command, this runs this R2 command, and so on. So whenever this is, one of these is changed, set format is called. Set format just changes that state, the format state. And then this effect here depends on the format. So this effect will run again. So it will then execute the R2 command for that specific format at the address that we are in, that we're showing here. And now, if we go and look at the code of that again, in turn. Yeah, so this whole thing starts with load R2 at the bottom here. Which does load R2 module, and that's a generated function. So we're using the mscript toolchain to produce a WebAssembly binary. This has been done ahead of time. When cutting a release of this tool, so there's a make file that does this. It builds Radar, but uses the mscript toolchain to produce a binary. And then this generates a load, like a function. This module has a default export that just loads the module. And we're calling that, and we're providing it some callbacks that the C code can call back to us. So on the C side, so we're building our R2, and then we have a tiny program that implements an I/O plugin. So here we're just defining the callbacks, and there's a function, exported function called open, r2open. We give it the OS, the architecture, and the bits, and it just sets up the R2 core instance with using that. And then whenever, for example, the open IO plugin handler callback will create a descriptor, close similar boilerplate. But the interesting part is here, the read callback. So mscripten has this em async.js macro that expands, where actually you give it a return type, the name of the function, and the C signature of the arguments, parameters. And here the body is JavaScript. And this body here is actually can return a promise or be an async function. So here you can do something asynchronous, and that means we can interface with Frida with the agent in the far end process. But this is all running in the browser. So here we're doing await module on read. And yeah, that will communicate with the agent. And then just copying that out, the result out. Right, I haven't implemented that yet. That's essentially it. And then on the JavaScript side, it has implemented on read. Down here, too far. Yeah, on read is here. So when we're instantiating this WebAssembly module, calling the function that was generated by mscripten, the toolchain, we can define arbitrary properties on this object that we give it. And here we're defining onRead, which this IO plugin calls. And yeah, here we have a simple IO cache, because I still need to figure out how to get that working correctly in all cases. So that's temporary complexity. But yeah, here we're calling basically a read. And then the user of this package needs to provide the read. So it's not really tied to Frida at all. You could read from something else. But the feature set that Radar was built with is tied to Frida. That's why it's in the Frida namespace on NPM where this is published. So I didn't want this to look like something to be used for all use cases. But because we're building R2 with exactly the plugins that Frida needs, so we're limited to the architectures that Frida supports. And that means we have a fairly small footprint. So for example, PyPy. I can just download Frida tools from PyPy, I guess. Yeah, so it's a 4.6 megabyte download. Oops. Frida tools. Oh wait. And so inside the Frida tools package from PyPy, you can see that there's the tracer, which we're running here, frida-trace, and then there's the agent, which is injected into the remote process, and then there's a tracer UI, which is the browser part that's running in the browser. And if we extract the UI, you'll see here in assets that there's R2 WASM here. So all of R2 that is running in the browser is only 8.7 megabytes, which is pretty good, considering that it supports all the architectures Frida supports and has capstone and so on. But yeah, that's basically how the IO plugin works. This UI is still in the early stages of development, but hopefully, so it doesn't have export, for example, and doesn't have a way to load a save. So yeah, lots of areas for future improvement, and the UI has quite a few rough edges, but Just wanted to show you, so hopefully some of you might contribute to it to make it better or work for your use case. And yeah, any questions? All right, thank you.
Let me have you. Like this. Whoa, whoa, whoa. The scissors here. Whoa. ¿Seguro? Okay.
Thank you.
You're welcome.
Thank you. So, which laptop? Like that one? Yeah, there's no problem.
They will be enabled in the next seconds. Is this your background? Yes? Okay.
If you can extend, I duplicated, I think it's better than extend.
Okay.
Yeah, just connect it and just duplicate the screen and get that resolution and I think it's better.
Ah, yeah, maybe. No, but it's not.
Okay. Just a minute?
Yeah. No.
Is it possible just to duplicate the...
Yeah. Yeah, I think so. But we have the notes.
Ah, okay, you have the notes. Okay.
But no, it was okay.
Morning, morning. We are preparing the computer for the next presentation that will be uncovering more crypto secrets. So hold on for a few seconds before we can fix.
Ah, là c'est bon.
Any IT guy in the room?
No, it's okay. Ah no, no.
Donne-le-moi, je vais le passer ici.
No, it's okay. you have it.
Yeah, but I need just a connection on my phone. Yeah, okay. That's good. And then resolution is not. I will just try.
Beep, 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 beep. Boom! Applause, 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 applause! Nice! Room is yours,
Okay.
guys.
Okay, sorry for the waiting time. So it's really nice to meet you in person, finally. That's really good. And welcome to our talk, Uncover More Secret, Crypto Secret with Radar 2. Before we start, just quick, I'm Sylvain. I'm an applied cryptographer at Delic, so I'm mainly doing with cryptography, trying to break implementation of cryptography algorithm and protocol. I will be there today and tomorrow, but if you want to contact me, you can do it on Mastodon, and I will let Karim present himself.
So I'm Karim Sudki.
Oh.
Is it okay?
Does it work?
Yeah. Does it work? No? Hello? Hello, hello. Hello? Yeah. Okay, good. Hopefully we don't have anything more. So I'm Karim Sudki. I'm an IoT security expert. My main area of expertise is hardware. So in my daily job, I do hardware hacking. I mainly focus on targets. It can be a small microcontroller, but also bigger system like EV chargers and things like that. And you can find me on social media via this handle in X or Twitter. So this talk will be about how basically we use Radar 2 for memory analysis. It has some nice features such as pattern recognition and also some nice things to recover cryptographic materials. It's also about showing you some evolution from the previous talk that Sylvain did back in 2020 about cryptography. And also it will be the occasion to show you some practical use cases that I use Radar 2 to recover some secret in real target scenario, let's say.
So if you have used Radar 2, you figure out that you can search for a lot of different things, just string, X pattern. You can search for if some hash digest match in memory to some hash of some block. You can search for magic constant in the memory. But for this talk, we'll mainly concentrate for the /C, so meaning that we are searching for cryptography materials in memory or in a binary. And when you search, you have in Radar 2 you have a lot of configuration you can change. Basically, you can tell I want to search from this address to this address. I want to stop the search after I hit, for example, 3 result. And you can find all this configuration in the R2 book. But it really helps you to configure your search in Radar 2. You can do more complex stuff that when you search, you have a result, you can execute a command on a hit, that's nice. But one thing which may be problematic is when you want to have more advanced pattern, like you want to match this string and this pattern, but not this constant. And for that, you need something more, you need plugins. And as Pancake mentioned during his keynote, now, we have Radar R2 Yara. So Yara means yet another recursive acronym, so it does not really helpful to understand what is it. I think most of you know what is Yara, but it's basically an open source tool developed by Aristotle at the beginning. So basically you write a text rule, and if this rule match into your memory dump or your binary, then it will tell you that it matched and where. So it's really useful. It's used by a lot of tools like IDS, antivirus, and even yesterday I discovered during the training of Travis Goodspeed, which was really good, that it's also used by mass-crom tools, so to create rule to search into a mass-crom. So it's really, really nice. And in R2, so you can use Yara as well with the R2 Yara plugin. So this is an example of a rule we will use during this talk. So it's really simple. You write the metadata with the author, the description, the date, and so on. Then you write your pattern, like the base, here the base point. In hexadecimal, you can, so there's a lot of ways to describe your pattern. I really encourage you to have a look to the documentation. And the most important part is the condition. So basically, you define what is a logical pattern you want to match. So here we want to match the base point and one of the two coefficients. So it's really powerful. It will really extend your search capability in Radar 2. So as usual, you can install R2 Yara with the package manager from Radar 2 with this command line. And the new thing is that now R2 Yara moved to a separate repository. It used to be an extra repository. So now if you want to have a look to the code and contribute, this is to this address you have to go. I will show a quick demo just to show you how it works. So basically, we open the binary. Then there is a preloaded rule already in when you run it. So here I'm just clearing the preloaded rule. So all the commands are YR command. Now I'm adding the rule I showed you before. I list the rules which are loaded, so you can see that there is two rules now. And I can just scan my binary, and I got a match. So it tells me which rule was matched in the binary and where it happened. And then it created some tags, so I can seek to those tags in memory, and it will stay during my reverse. So it's really helpful, because as soon as you, for example, here, you discover that this binary is using cryptography algorithm, because you could identify the constant. So now you can reversing from this part in the binary, because you know that it uses this algorithm. So it can be really, really powerful depending your reverse. Yeah. So of course you can reuse some rules. I used to work with one repository called Yara rules. There is a lot of rules, not only for cryptography, but it seems that now it's a bit frozen. The last commit is 2 years old, and there's a lot of PR which are not merged. So just for waiting, I created my new repository, especially for cryptography rules, because that's the one I use most. So if you want, I will integrate your rules, and maybe the new repository will come back to life at some point. And the new one novelty, thanks to Pancake, is that now you can create your own Yara rule while you are reversing directly into Radar 2. So the commands are YRG. So that's really helpful because you don't, I mean, if you find a pattern in a binary, you can keep it in your current rule and then reuse it while you are reversing. And it's quite easy to use. I will also show a small demo. So again, I open a binary. Then let's assume I found, I found a nice string in my binary, and I say, oh, I want to keep that into my rule. So now I delete the rule again. I type YRG to see what is the current state of the rule. And now the rule is basically empty. I have only the metadata. So the rule is just, I can start working with that. So I will add the string I found at this address, which is 16 bytes. Now I will display the rule again with the same command. And now you can see that the pattern is written, and the condition is all of them because I have only one pattern, so it will match all the patterns. You can configure your rule. So here I'm just changing the name. For example, you can change a lot of things like the condition and so on. Now I will add this rule I just created to the loaded rule in Radar 2. I can list to check that it's already loaded. So you see that the name was updated. And I can use it as before as a standard rule. So it's quite convenient because you can just keep track of your finding during your reverse and use it in a Yara rule. Okay, now let's see what happened since last time about symmetric cryptography. So maybe you remember in 2020, I was presenting a command called /ca, which allows you to search AES key schedule in memory, because for AES you have some relation which will, if you have a memory dump with an AES key schedule in memory, it will allow you to find this key schedule easily, just with /ca. It turns out that we needed this feature, but for SM4. So SM4 is a Chinese standard for a block cipher, so it's the AES but in China. So we decided to implement the same feature for SM4. So now you can just use a parameter to scan, to do the same, exact same thing for SM4. And we presented the result we got with this, about SM4 on some hardware attack with Baldar, another friend at Hardware.io. So if you're interested by this in particular, I really encourage you to have a look to this presentation. But for R2 user, maybe one thing to mention is that for SM4, there was one thing a bit different. Like for AES, the secret key is directly into the key schedule. For SM4, it's not the case. You first XOR your secret key with some constant, then you do one round of encryption, then you discard, you get the first round key and you discard the first secret key. So it means that you will find the key schedule, but the key is not present in memory. But you can forget about this scheme because we just added in Radar2 a small message which will reverse this run and display the correct key value for you, so you can reuse it without bothering like what is the key value at the end. But still in memory, you can see that the first round key does not match the secret key. So that, I think it can be also helpful for you. Also, while we were working with Karim, we use a lot the WOD and WOE command, which will take a block and write over this block its decryption or its encryption with an algorithm. But we figure out that sometimes we don't need to directly write into the binary, but just check what is the decryption of this block or the encryption. So we added two simple commands, POE and POD, and you can just use them to print the decryption or encryption of the current block of your binary. And here is the current list of the supported algorithm. You can just print them in and see what's supported. And so that was the theory, and now I will let Karim explain how he used it for real project and how it can be useful for practical application.
Yes, so once I came to work and basically customer gave us a device that I need to have a look on, and this device turned out to be a standard PC, let's say a big PC with FPGA connected and other things. It turns out that this PC was using a Linux operating system, nothing fancy about that, but it had a lot of features enabled, such as secure boot and full disk encryption. The nice thing about full disk encryption is that they were using this trusted platform module. If you are familiar with it, it's fine. If not, it's just a hardware component where you can send cryptographic materials and it would be stored in a secure fashion, so you cannot retrieve it without having the correct conditions. And the goal was obviously to first decrypt the disk and start to have a look on what's inside the system. So just to understand a bit how it works, so basically if you want to encrypt a disk, you will seal a key or a passphrase, which is not the master key to decrypt the volume, in the TPM. And during boot, what you will do is the system will measure each component that will be run on the system, and it will compute a hash that will be stored in a register, which are called platform configuration register. There are up to 23 of them, 24 actually, but some of them are used for user usage and others are for the system. So, for instance, PCR0 is used to measure components such as the BIOS and other firmware components. So you will have the hash and it will be extended with all the components. And for instance, PCR1 is used for the configuration of the BIOS. So whatever configuration that you had in the BIOS will be hashed and stored in this value. And it turns out that the key is released only if the PCR matches. So the condition for this specific use case is that you provision the key when you boot the system and you know it's trusted, in a trusted state. And then you will ask the key whenever the system was booted without tampering. So it means that if you change the command line or you add some things or you try to tamper with the device, it will not work. So disk won't be encrypted and you will be having a nice message on the screen. So on a practical perspective, it's fairly easy to do. There have been a lot of noise around it. It's a simple and low-cost attack. Basically, you can either do it very cheaply by soldering wires on the pins, because since it's a component that sits outside on the motherboard, you can do it. Some guys did tools. So here you have a tools from Stack Machine that fits very good to this connector on this laptop. And what happens is that once you are set up, you will just monitor the signals with the logic analyzer, wait for a specific command, it's the unseal command, and then you get the key. So on the right side, you can see that there is a Pico TPM sniffer, it's the tool above, and you can see that the guy recovered the BitLocker key in a few seconds. It took him, with the tearing down of the laptop, 43 seconds to get the key. Of course, then you need to do some things on the disk, but it shows you how easy it is. However, on my setup, the TPM is quite different. So TPM is not sitting just like this, which is called discrete TPM, but in fact, it's incorporated inside the CPU. So on Intel, it will be platform trusted technology, sorry, and on AMD, it's called FTPM. So at this point, I was quite fed up. So where I can put my probe, what I will do, because I cannot recover the signal easily. And at that point, I said, oh, smart move from the customer. So then I started to wonder, is it really a smart move? Can I do still something? Because maybe there's other ways to get inside and recover the key. So luckily, the BIOS password was not set. Don't ask me why. And as I explained before, the BIOS settings were not measured as part of the boot process, which means that you can modify these settings. So then you ask the question, what shall you modify? And can I modify, for instance, secure boot? Unfortunately not, because if you modify something in the BIOS or reset the BIOS, you will erase the key and it won't work. Then you say, oh, there is nice features such as Intel VTD. VTD is for virtualization technology. You use it when you need to run an hypervisor, for instance. And what happens is that when you enable this feature, it will enable the IOMMU, which allows you to separate the memory and isolate each memory region for the others. So this means that you can do DMA attack. What is fun in this specific use case is that the Linux operating system was installed using UKI, which means a unified kernel image, and therefore you cannot change the kernel parameter because it's encompassed inside the image. So in this case, they didn't have Intel IOMMU on, so it's even easier. You don't need to disable Intel VTD. It will not be taken into account. So to do direct memory access attack, you just use some tools. There is one that works pretty well. It's PCI Leech. So you plug it inside the PCI slot, you boot the system, and you connect your laptop with this device using USB-C. You'll launch some commands. The FPGA will do the thing and dump the entire memory for you. And then you use your favorite commands in r2con2024 to find the key expansion in memory and decrypt the disk. So here I prepared some small demos. However, it's anonymized, of course, and I did it on a VM, but it works in practical the exact same way. Bear with me. So here, for this demo, I just narrowed the search because I know there is only 2 hits that I need because my system was using XTS 512, so this means that you have 2 different keys that are being used with 256-bit encryption keys. And once you recover them with a r2con2024, you can just reorder them and decrypt the disk. One other nice trick is that for crypt setup or those setups on Linux, usually when you have an offset of 0x1f0, this means that you have the 2 key expansion for the disk encryption, if it's using this thing. This can be also seen if you dump the LUX header. Once you get access to the system, you can see that the bytes match. So you will have first key and second key on the second row, and then you can access the disk. If you turn out to access a Chinese system, this will work the same way as Sylvain mentioned previously. In this case, it's also the same story. You use 2 keys for the encryption. I don't know if there is any pattern for this one, but you can see that we recover the key. And if you look closely to the bytes, you can see that the LUX header match as well. So this means that you will decrypt the disk and get access to its content. Then you can perform usual stuff, like reverse engineering the binaries that lies on the top of the file system, the application of the customer. And of course, this led to some discovery. So there were multiple RCE as root on the system because it was badly coded. So just to see the impact that it can have. So now we'll switch from symmetric crypto to asymmetric crypto. There are a few things that you can do as well with Radar 2. You can search for certificate. You can search for private keys as well, or other keys and signature for GPG or PGP. It's quite convenient. You can also, when you have a hit, you can use the PF whatever commands that will display you the decoded version of this. So you will see it in a human fashion, in an understandable fashion. And it's quite convenient. So for this target, so this particular use case, I had a device. It's a standard IoT sheet where you have an ARM microcontroller. And it turns out that those guys let UART console, serial console, open, no password, nothing. And there was a shell, custom shell inside, where you could run some commands. So you could read from an arbitrary location and write to an arbitrary location. So I used it to dump the microcontroller firmware and then to dump the external memory as well, because it was free, so I use it. On the external memory, on such devices, you often see that people will store specific assets, such as certificates, settings, whatever. In that case, the device is connected to the cloud directly via Wi-Fi, so without any application, because usually you will have your app that will do a proxy, get the data out of the device and send it to the cloud. Here it's direct connection. So often what I do is just, I fire Radar 2 and I just hunt for certificates. So this is what happens when I do it on my memory. So I just load my memory dump. I switch the block to a bit larger than usual, by the default one. Why? Because it will be used further on for the print commands. If you don't do it, you will have a nice error message. So I just increase the block a bit. I can range it even more if needed. And when I do /cr, so it's to find the private key, I find 2 hits. So at this point, I'm like excited. However, if you use the command to print what's really inside, you can see here it's actually a template. So it's a certificate request, and it's a certificate request, this one, and the next one would be a template for a certificate. So it's not useful. You cannot do anything with it. So then I fire /cd to search for a certificate. I have a hit, and then I will use again the command to print the thing. So on the screen, you can see that the command name actually is a MAC address. Here it's anonymized, of course. We can see the validity of the certificate, and we can see there are several fields. Here there is a public key, so we can confirm it by just running the pfx command on the same offset, and you will see that it's using also a curve, ED25519, and I was not quite I didn't have any knowledge on this, so I found this public key and I was like, okay, that's fine. And before going forward, I think it's up to, so, yeah, sorry. So I found this public key, but I didn't find the private key as we saw before. So /er didn't find any private key. What you can do is when you have a memory dump, to give you an indication if it's encrypted or not, you compute the entropy of the binary. And then you can see on the right side that the blocks, the entropy is not that high. I mean, if it's encrypted, you will see it's super high all along the binary. Here it's like just a few of them, and maybe it's even not encrypted or not just compressed some part. So, okay, then I went back to my firmware. I started to reverse engineer my firmware. I saw some pointer to the external memory, but still, I was wondering why I could not find the private key with /tr. So I turned around to my friend Sylvain, and I asked him, yeah, how can I find the private key easily?
So first, maybe the ED25519 algorithm, maybe it's not well known, but it's quite used a lot in embedded device world because it's basically like ECDSA, but you don't rely on the random number generator. So basically, you won't have all the vulnerability like the PlayStation 3 epic fail. It's quite small. The code is quite small as well. The key generation is fast. And also you have small keys and small signatures. So it's more and more used in the embedded world. So maybe you will see it during your project. And we were discussing with Karim because he told me, okay, I have the public key. I'm almost sure the private key is in my binary. So what can I do without reversing everything because it's a lot of work? And we were thinking, okay, you have the public key, and you know that the public key is the private key times G, and G is just a base point. It's defined in the EDDSA standard, so it's known. So a stupid idea, but you can just take your memory. You assume that the first byte up to the 32 first bytes would be the secret key. You multiply by G, and if it matches the public key, it means you found the private key. And if not, you just continue as a sliding window until this relation is matched. And if it's matched at some point, it means that this is the private key. So I told Karim, that's the idea, go, implement it.
Yeah, just do a multiplication. However, for me, it sucks big time. Like, what the fuck those cryptographers are doing? How can I can sort myself out? And then I decided just to go for this Python script. I don't give a shit. So I basically loaded the public key. Then I used the sliding window mechanism, just taking 32 bytes at a time, consider it as a private key, compute the public key, and compare the results. And whenever you have a match, boom, you can see it was found at this offset, which is just before, located before the public key that I found. Then I was starting to wondering, because usually my best teammate here loves r2, so I said, oh, maybe this feature can be useful to others. And then I asked for a feature request to the crypto team, meaning him. And yeah, and then he says, oh yeah, let's add another command to r2. There is not enough. So he just generated a PR and done.
So, ta-da, there's a new command, /cp. So basically, it will just allow you to search, if you have the public key, it will allow you to search the private key in your binary, just tapping /cp, the algorithm parameter, and the public key. So far, there is just ED25519 supported. As always, PR are welcome. Maybe in the midterm, the goal would be to support SSL algorithm, so that you will have all the signature from OpenSSL. As usual, if you're not happy with this feature, we will refund your premium license to all of you, no problem. And also during this project, we also figure out that it's sometimes nice to be able to print the signature of a block. So we also created a POS, so it will print the signature of the current block with the algorithm and the private key for this time. So yeah, it's something you can already use now in r2. And yeah, I will let Karim show how it worked on his project.
So basically, I took the same example as before. I just put the max hit because we know that there is one single private key, and if not, it will run forever. So again, we just do /cd, we get the hit, we print some, we print this, and then we'll seek to a specific offset. I will explain a bit what's going on here. So here we go to the offset of the public key, which is 0x81. Then you have the header of the ASN1 structure that you need to skip. And then because it's a bit string, there is an additional 1 byte that will be added for sign of the value. So I need also to skip that because the value that I want is actually starting with F0 whatever and 32 bytes. Oh, sorry. I mixed up the commands. And then, so I will just seek to that offset and use the 32 bytes that are at this offset to search for the private key. And as you can see, you can find the exact same private key that I showed before using r2con2024.
Applause.
So this allows me to recover the public and private certificate. This device, I could impersonate it against the cloud, which was quite useful because firmware updates, for instance, were protected, so you couldn't access it publicly. So it was nice. I could also fake telemetry, and I can do further attack at scale because now I have access to the cloud, so it's quite convenient. So we hope you enjoyed the talk. We wanted to show you that r2con2024 can be used in many situations, not only binary analysis. We hope that you had a good grasp on the evolution of the cryptography related commands and that you will use it in your upcoming projects. We would like to thank you for the attention, also Pancake for the venue, and if you have any questions, just if we have time, we can answer that right now or later on during the conference. Thank you.
It was clear.
Cryptography is clear. Okay.
Thank you.
Hola. Hello, hello. For all the speakers, we have a small gift outside, so.
Let's try the other. Oh, no, this works. Okay, cool.
When you have like 5 minutes left, I will show you.
Okay.
Just to make sure that we
Well, I think I should be shorter than the time I'm allocated.
Okay.
So.
Don't worry. Take the time you need, but just in case, I will be with the iPad with the timer.
Okay, thank you.
Let's wait for 5 minutes, okay?
What should I do?
Thumbs up. No. Because it's Italian. Everything?
Welcome back. Okay, it's a pleasure just to present Francesco, or Mr. Macete. He's working at Now Secure as an iOS security researcher, and he's going to talk about iOS and his internals, and he's a super expert with R2 and iOS, so just enjoy the talk. Thank you.
Hello. Does this thing work? Okay, cool. So, well, I'll be talking for about 1 hour about Frida hooking on non-jailbroken iOS. This is nothing particularly new. It's just an overview of what we can do right now with what we have. There's no artificial intelligence in this talk. So my name is Francesco Tamagni. I work in Now Secure in the research team with Pancake and Ole, and I contribute to Frida and R2 as much as I can. What I do in the research team is trying to help automating iOS dynamic analysis of applications. That's my GitHub, and those are my nicknames. when the jailbreak is available, Frida takes full advantage of it. But when it's not, it's still possible to use it on iOS with some limitations I'm going to talk about. So I'll be basically in this talk, I will be placing hooks on system library code, but from within the process, the context of an app process, because that's the first limitation. So without jailbreak, that's just what you can attach to. But still, there's the possibility to explore the system library code with at least the part which is reachable from within the app process and the boundaries of it. So I will do this with a lot of help from R2. I already gave this talk in another conference which was shorter, so if you already saw that at the time, this time there will be more R2 into it. I'm gonna do live demos all the time using a simple, stupid test app I wrote, but actually all I talk about will be applicable to any repackaged app in general. So in the live demos, I'll be applying the same hooks to achieve the same result under the 3 different scenarios of increasing difficulty. So the level 0 is the easiest, where the app is launched via debugger. In level 1, we will have no debugger involved, means that we have to launch it manually. That's when you don't have control of the app lifetime when testing it. And the level 2, still no debugger, but we'll have to deal with pointer authentication. So, so when we launch an app with a debugger, we have no code signing enforcement on iOS, which means that this is much similar to the jailbroken case, in which interceptor can actually change and create code in memory, and so it can be used extensively. And also, Frida, in this scenario, is able to inject itself into the target, so there's no need to embed the Frida gadget ahead of time if you're going to spawn the app with a debugger. And also in this scenario, the instrumentation is quite early, so you can still capture all the early activity of the app and its frameworks with your own instrumentation. So in order to do this with Frida command line tools, you just have to get the Frida gadget from the Frida releases pages and put it in that place in your home directory with that specific name, so that Frida command line tools will pick it up automatically. So then you can spawn the app using Frida command line tools if the app is debuggable, which means it has the get task allow entitlement. Frida will be able to launch it using LLDB, inject the gadget at runtime, and detach the debugger right after that. So let's take a look at this stuff practically. So this is the app, the test app, which is very stupid. It only has 2 buttons, network and files. And this is the whole code of the app. So if you press the network button, it will make a GET request to Google using the NSURL session task. If you press files, it will open ATXT and BTXT inside the temporary directory for the app. The ATXT will be opened using the open function, and BTXT will be opened using the NSFile handle Objective-C class. And so in terms of hooking, we want to hook so that we print the paths of the files, the full path of those files that the app is opening. And for the network part, the hooks will be dumping the boring SSL session keys for the request. So that's it. So these hooks are very simple, but we will do this in all these 3 scenarios. So let's look at the code for the level 0. So the level 0 with the app is debuggable. I'm not good at typing while speaking, so I already wrote the scripts. So it starts from here. The RPC exports init, that's where the entry point for the Frida script is. and it will call these two functions that are applying the hooks respectively for SSL and for open files. So let's start from the files. This is a simple interceptor hook. So it will just hook, attach to the open export, and on the onEnter it will just get the string on the arg0 pointer and print it. In this case, log is just console log. It will become more complex later. Instead, for OpenSSL, for boring SSL, we have this, which is pretty much what you can find in Google if you search for boring SSL dump TLS keys, where we want to call this function, SSL-CTX set keylog callback on an instance of SSL-CTX, to pass it a callback function, which will be called back with a line of text, which we just print. So in order to do so, we make sure the module, the boring SSL module is loaded. We create a native function so that we can call that function, which we resolve using a debug symbol. Now we have to find a way to call this function on an instance of SSL-CTX. And so in order to do it, we just attach to SSL-CTX new. So every time an SSL-CTX is created on the onLeave, we have the pointer on which we want to set the keylog callback using that function. And the callback is just a native callback, which takes two arguments. The first one, we don't care. The second one, it's a string that it's pointer to a string that we read and print. We have to keep it alive so that we make sure that the JavaScript garbage collector is not killing our callback before boring SSL wants to call it. Otherwise, it will have a dangling pointer and cause undefined behavior, which is not great. And that's it. So this is the whole code for the hooks of the level 0, and then we can just show this. So this device, this is my device, which is a iPhone SE 2020 with iOS 18.1, non-jailbroken. So I can just spawn the app like this, like normally, and Frida will pick up the gadget and load our hooks. Of course, the first time it fails, but that's because of the pre-worm. I have to just do it again, and it works. So now the app is being spawned, and the hooks are being applied. And we already see that the app just started up, we didn't do anything, and we have a lot of noise from the open hook. And that's because we have early instrumentation, and open is actually hooked in memory, so the interceptor will be hit. The interceptor hook hits for all the calls from within the system libraries that run during app startup. So we see a lot of noise. It's not important, but it's good to note, because that won't happen in the next scenarios. But if I press the files button, then I have atxt and btxt, and these are the ones that we want to see, and we have the full path for them. And if I press network, we see the oh yeah, so it needs internet, but wait a second. I need to redo this by connecting to actually my hotspot. Yeah, they should work. Yeah, there you go. So here we have the keylog from our callback with all the boring SSL keys in hex. So this is what we want to recreate also on the next scenarios. So let's see. So level 1, we will have the same app, but we're not going to use the debugger. So we are going to spawn the app manually. In this case, we won't have, so we will have code signing enforced. And so this means, first of all, that we can't, we have to embed Frida gadget ahead of time. Because we can't create, Frida can't create or modify the code at runtime And also, interceptor won't be able to work as it works normally because it can't change the code. And so, if we take interceptor out of the picture, we're left with function pointers, basically. But that's still a lot, because you can still do a lot of stuff with native callback and native function, because native callback still works with consigning enforcement, because Frida uses libffi closures under the hood, and that's code which is already signed, which is mapped multiple time in memories along with data pages, so that you can configure it at runtime, but the code doesn't change. And the callback implementation, it's in JavaScript, which is in fact data, so it's not a problem for the code signing perspective. And we can use native callbacks and native functions to override pointers and call the original implementations, so we can still do swizzling in Objective-C methods and blocks. We can replace pointers in C++ vtables. We can replace generic function pointers in structures, and even some Swift if you're brave. But the braveness comes from the fact that you have to be careful about calling conventions, because if the function you're replacing hasn't got a calling convention supported by libffi closures, you have to bring your own translation gadgets that we also have to sign ahead of time. So I'm not going to do that in the demo, but it's totally doable. On top of this, another possibility is to use gumgraft, which allows some interceptor usage by preprocessing the binaries of the app statically before signing them, so that it can apply some of the instrumentation that the interceptor should have done at runtime, and it can't. So it works like this. It's a command line tool, part of frida-gum, which takes a single Mako binary, and you can tell it what to hook, basically what to prepare hooks for. So you can ingest all the imports. In that case, you probably want also to transform the lazy bindings in normal bindings, so that all imports are hooked the same. And also, if you need it, it's possible to specify absolute offsets from in the binary itself, or ingest all the function starts in the binary. But those two options are a bit dangerous at the moment. It can be improved because at the moment there's no code relocation implemented in gumgraft. That means that if you place hooks in the binary itself, those instructions where the hook is placed are moved away somewhere else. But if those instructions have some PC relative reference, that will get broken and cause undefined behavior. So you can do this if you know that you're not causing this problem, but in general it's very hard to know ahead of time unless you already know all or what the binary does. So yeah, it works like this. So by adding segments at the end of the binary before linked, in this way the text to data references are fixed. We just have to update the references to linked, and these segments will contain the trampolines and the configuration needed for them. Much like libffi works at runtime, pretty much we do this at static time, ahead of time. And the more hooks you will place, the more segments you will have, and that's it. So if then the binaries of the app are prepared in this way at runtime, interceptor will pick this up automatically, so you don't have to do anything different in your code, and interceptor will work for the things you have prepared the grafting. So let's try this. But first, okay, so let's run the app for the level 1 manually. In this way, I can still. So let me show you the app. This is not this. So yeah, so this is the same code, but it will have a run script phase that runs gumgraft on the imports on the main binary. And then we have the gadget embedded here, configured for code signing required, which means that even Frida itself can't rely on interceptor to be able to change the code. Type listen means that now I launch the app manually, but we can still attach to it using Frida command line tools. And onload resume, because we really don't need early instrumentation, so as soon as the gadget is loaded, it just resumes the app. Yeah, so we can try now to attach to it. We can see it. We see the app, which is both as gadget and as the app itself. But yeah, so I can attach to it by name. And we can try to load the level 0 hooks in this scenario and see what changes. So now hooks are applied, but if I press files, I only see A. And if I press network, I don't see anything at all. So this is the level 0 hooks with the app launched without a debugger. And that happens because, so we see a.txt, because that's the one opened directly using the open function, which is imported by the app. So gumgraft was able to pick it up, to actually instrument it. And so the hook, the interceptor hook to open will only hit for that. But v.txt, even if an S-file handle uses open under the hood, will not go through the import to call open, because it's in the dwld cache, so dwld cache code calls dwld cache code directly and doesn't pass through the gumgrafted import. And so in order to still get the path from v.txt, we can just use Objective-C implement to swizzle the Objective-C method. And that's good because we can, so we can just, that boils down to using, to use a native callback to replace a function pointer. And so we have no depth problem here. We can hook private stuff in the dwld cache in this way, and there's no problem. And so that's what I'm going to do in the level 1 for the files. So just looking at the files for now, the interceptor hook, we can keep it because this still works for a.txt. But for b.txt, we can get the method that it's the one used by the app. We just save the original implementation, and then we set the implementation to a new one, which using Objective-C implement. So we can get the path again, which this time is an Objective-C object because it's an NS string, and then convert it to a JavaScript string and log it. Sorry. For SSL, it's a bit more complex. So the problem is the same. We had a hook with interceptor to hook SSL CTX new in order to get the pointer to the SSL CTX instance. We want to set the keylog callback on, but this one is not going to work for the same reason. So it's not imported directly by the app, so gumgraft can't do the trick, and we have to get creative with function pointers. So we have to find a function pointer which gives us access to the same instance, and that's called early enough to set the keylog callback before the handshake happens. And so, well, we don't have to look far, right? Because Boring SSL is open source, so we can just, if we look at the argument of SSL CTX new, we see that it's a structure which holds a pointer to another structure which holds a bunch of function pointers that are very promising, especially the first one looks like one which should be called very early. And but we can see the same in R2. So let's look at this in R2. In order to do so, I have to open the DWLD cache with R2. So I have here the DWLD cache for this phone and this iOS version downloaded, which is also, if you're not familiar with the DWLD cache, so all the system libraries in iOS are not in the file system by themselves. They're just linked all together in a single big executable that's then mapped in all the processes. You can get these, for example, from the IPSW files. And in recent iOS versions, this is also split. So like in this case, you see these are 60-something files which contain all the libraries from iOS user space. And we can open this stuff directly using R2, using the DSC IO plugin, which I wrote. And you just have to point it to the first of the files, which is the one without extension. Now, there are thousands of libraries here. And so if we just open it like this, it will take a lot of time to symbolicate everything and load all the maps and so on. So there's this trick using an environment variable called RDOLD cache filter that you can pass. You can set with partial string matches for the libraries you're just interested in, and so that R2 will just load symbols for those and strings and so on. You still have the whole DWLD cache mapped, but you will have information only about those libraries. So now if I do this, it prints all the libraries which are actually matching the filter and their direct dependencies, so that we can navigate a bit in the code. It will take some time, but not terribly much. And what happens in the end is that it's like opening a single macro executable where each of those libraries are contributing their own macro sections to the big executable we are opening. So the flow in R2 is the same as usually. So what I want to do now is to find the caller to SSLCTX new so that we can inspect the arguments to it and dig those function pointer that we want to replace. So what I can do, if I do IS, there are 2,000 more sections because all the libraries. I'm just interested in boring SSL. So these are all the sections for boring SSL. I don't know if you can read anything about this. I can zoom in more, but it becomes messy. But I just need the text section right now. So I can just seek to the text section and emulate it using AAEX. So this means AAEX will emulate this much bytes. $SS means section size bytes at the address section start. AAEX we just emulate for the purpose of creating the cross-references, so it will be very fast. So we just emulate this section, not all the code in the DWLD cache, and so that we can find references. Now, I want to find a call to SSLCTX new, and which is this one. I can use AXT, analyze X references too, and I can use the address or the flag equivalently to get the call to it. There's only one call in boring SSL to this, and so I can just seek there and go visual and P. So, okay, so this is the call. We want to inspect the argument 0. In this case, it's just x21. So I have to figure out what x21 is. And normally do this. I highlight x21 and scroll until I see something using it. In this case, these high registers are usually storing arguments, so I can just be confident and scroll up. There you go. So this is the beginning of the function, and we see that x21 is actually x2. So the argument we are interested in is actually the third argument to this function. So I can just, we have two references there. I can just press X and 0 to get to the first one. And so we can scroll up and see what x2 is. x2 is the result of this function call. So I can just go down there and see that this is actually creating a global reference. So basically, this argument is just an instance of a global variable, which is stored at this address. It also comes with its own symbol. And so if I go back, well, I can just do go there. Let's go there. It's not code, right? So this doesn't make sense. So I can do B and W and move to the PXR hex dump, which is the periscoping view. It's in this. So this is a bit too zoomed in to actually make anything out of it. So I can just do it here, which is equivalent PXR24. And so I can say this is, if I can compare this with this, so there's, it's a pointer to this structure, basically. So we get some version, then 2 pointers, and that's what we get here. So we have these null bytes, which is probably the version, and the method pointer and the x509 method pointer. So we're interested in this one, the first. So we can also go there again. And we're still in the periscoping mode, and you see that the first one is the TLS new. So this also has symbols. So basically there's this, we can just resolve this symbol by name. And we get the pointer that we want to replace, and this is where it's stored. So basically here we are in the outconst section of boring SSL. So now we have to design our Frida script in order to find this pointer and replace it. So now we know that there is a symbol, so we can resolve this symbol, get the address, and we know that it's stored, this pointer is stored in this section, so we can use the search to do this. So we can also simulate this in R2. So if I do search in equal bin section, means that it restricts the R2 search in this current section, which is outconst of boring SSL. So if I know the pointer to search for, I can just use the /v8 command, which means search value of length 8 bytes. So I can pass just the pointer and know that it's there. This is where the pointer is stored, which is just here, right? But this is something that we can translate directly into Frida, into Frida code. So this is what I'm going to do here. So for the new SSL hooks, so this part is the same. So we still load the module, get the native function to call, create our keylogger callback, keep it alive. But now we can resolve the TLS news symbol, find where it's stored, find the slot, which is the address where it's stored using Frida search. But and we can do this exactly like we did in R2. So we enumerate the sections of boring SSL, we get the outconst range, we search it with the pattern created from the pointer we want to search for. So now that we know the pointer and where it's stored, we can just create a native function so that we can call the original one and create our callback, which I will go to the implementation a bit later. But so we have the replacement, which is a native callback, and then we keep it alive as well, and we write it. So this write pointer safely just does write pointer on this slot. just making sure it's writable first and putting it back the original protection, if not later. But so now we replaced the pointer in the structure with our own callback. So what's missing here is to know how to get the CTX from this, because this is not directly the pointer we're interested in, but it's almost that. So basically, this TLS new gets an argument of type SSLST, which in turn has an initializer which take SSL CTXST, which is what we're interested in. And if we look at this initializer by going there, P, we see that the first argument, this is a C++ method. So the x0 is the this pointer, the x1 is the first argument, which is the pointer we want. So if and we can see that it's stored in x23 instead that this pointer is in x21. If I highlight x23 and scroll a bit down, I can see immediately that here is stored in the this pointer plus 78. So if we have that pointer, we can just add 78, and if we read the pointer there, it's the pointer we're interested in. And so we can call our function set the keylogger, and that's it. So we can try this. So now the app, I don't remember if this is the right one, but okay. So the app is launched, and I can attach to it again with the level 1 hooks this time. Yeah, hooks applied, and if I press files, I see them both because we had the Objective-C trick, and if I press network, we see again the keylog. Okay, so almost there. Level 2. So now we know that we can replace pointers anywhere and not violating code signing. Problem is that if your target is capable of pointer authentication, then you have to care about how you sign them, because if you replace a pointer, you have to do it in the right way, in the same way that the caller is expecting, because that's where the verification of the signature happens. By default, Frida signs with the IA key and 0 context, but let's look at PAC real quick, just a recap. So the PAC means pointer authentication code. It's introduced by the ARM v8 specification. This is very similar. This is the same as the message authentication code as a theory. So like you have the pointer, and in order to create the PAC, you get the pointer itself, some context, a key, and create a hash using a cryptographic algorithm. That it's just a small integer that then it's prepended to the pointer itself in the highest bits, which are unused otherwise. And so then now you have your signed pointer that before being used, it's verified in the same way. So the verification happens by providing the same context, the same key, and the PAC will be computed again, and it must match. Funnily enough, this picture comes from a paper attacking it, and not from the specification itself. So that's. So what we need to know is that. So we need to provide a key and a context. So in terms of keys, we have 2 keys for pointers to instructions and 2 keys for pointers to data. They have names because these names are actually part of the instructions that have to be used to sign and verify pointers with specific keys. So we don't have access from user space to the key data. And the context itself can be anything. And so compilers get creative. And so specifically, at least on iOS, So far, seems like normally C-style function pointers are fine with the default Frida signature, but instead C++ use a context which is created like in this snippet. So if you see that in the bottom, it's calling a function pointer. In x8, there's a function pointer. In x17, there's the context. And the context is just the slot where the pointer is stored, blended with this small integer, 6181 in this example, which is the diversity. There's even a function in Frida native pointer to do exactly this. But we have to know what is this diversity number and what key to use. And so how to do this? It's not, I mean, this stuff is, pointers are signed at load time by DYLD. And so this means that this information is actually inside the DYLD cache. It's not in memory though, because this information is stored in the higher bits of the pointer itself, so that at load time those will be replaced by the actual pointer, by the actual signed pointer. And that's also true in R2, because the IO plugin cleans up the pointer, and so we don't see that information even in R2. But there's a command in R2 which is able to retrieve this information by calling directly into the IO plugin. It's also possible to do that dynamically at runtime. I'm not going to show it, but you can. So this is still in the file of the DYLD cache. So if at runtime you know where the base of the DYLD cache is, you can just parse the metadata of the headers and calculate which specific file of the DYLD cache holds your pointer, where the offset is, and go read the file and get these bits out of it. So, so in order to show this, I'm gonna use R2. We have to add one hook though, so that we can use a C++. We can override a C++ method. If we override this one, we will be able to dump the key pair used for the Diffie-Hellman key exchange. It's not particularly useful. It's just it's a good example to show. So let's see the app for the level 2. Okay. So this time it's compiled for ARM64E. We still have the gadget, but to spice things up now, we also have the script embedded. So we don't even attach using command line tools. We will have, so the log function is modified to use an slog, so we can just grab the syslog for agent and see the output from our agent. This is configured in TypeScript. And this is the path of the script to load relative to the gadget config. And for the rest, is the same as before. So let's look at the code. But first, we have to find, let's find this. Let's use R2 to see this pointer and get the metadata. So we can use the same technique as before, actually. So we can go back to the outconst section. We can resolve that name, the symbol for that method. So if I do this, I'll see a bunch of them, but we're interested only in this one, the first one, which is the one actually called, turns out. But I can still use the V8 technique to find where it's stored in the vtable, and so this is the pointer where our pointer is stored. So if I just want to see it, is like this. But if I do :IP at the same offset, I can get the metadata about the pointer itself. So I don't know if you see this. So this is the diversity that we have to use to sign the pointer. This is the key. This is the raw pointer. This is how the pointer is actually stored in the file, in the cache file, and what we would have seen here if the IO plugin didn't clean it up and rebased. So the fun thing about the diversity is that it gives us a way to find all the callers to a specific virtual method, which is not, it's quite hard to do without. And so we can show also this. So I can go back to the text section and use the /AI command, which is not artificial intelligence again. And instead means search assembly for immediate, and I can search this diversity. I'm not in the right section, of course. I have to go to the boring SSL text section and do this command again. And these are all the call sites for this specific virtual method, which if you go in one of them, it's not clear. You know, if you didn't know that this was the diversity for that method, you don't know that x8 is that specific method, right? So like, this is very useful for reverse engineering. But yeah, so apart from this, let's look at the code. So we have this log dh offer function, which pretty much this is the same that we did so far. So we find this method pointer using debug symbol. We find where it's stored in the same way as before, just with one little change, that we have to mask the pointer. So this is a mask that will be applied to the pointer when searching, because where it's stored, it's signed differently than how Frida returns here. Because with debug symbol, we return the pointer signed with the default key and context. Instead, here in the slot is signed differently. So we can complicate this function a bit to just use the search pattern with mask, which works exactly like R2. So you have the hex of the pattern colon the hex of the mask, and the mask is computed with the one which I passed here. The only thing is that Frida is a bit picky, and it doesn't want zeros at the beginning or the end of the mask, so we have to take account of that. But that's pretty much the same code as before, plus a mask. So once we know where it's stored, we can do the same trick as before. We get the original native function to call the original. We can create our replacement as before, and then we can, but then now we have to resign it. So we can create the proper context. So we have the slot blended with the diversity, and we can strip the signature from the native callback, the default one, and replace it with the right one, with the correct context, and write it back again like before. So, well, the implementation will just call the original and then dump the key pair. I'm not going to too deep into this, but basically, so the argument you have in this method is so you can just get this pointer, and at offset 8 we have the private key, and so we can use this function to get the public from the private and then dump them. So let's see this in action. So we don't have to attach, we have just to use iDevice syslog and grep for agent, and then launch the app. So yeah, so this is the pattern. I was printing the search pattern just to show. So the pointer and the mask. And now if I press network, we should see alongside the keylog, which still works because this was just C function pointers. We also have the private and the public hex dumps. Yeah, so that's, I think that's it. So. Any questions? See? Yeah? Sorry? Yeah. Yeah. So the key is you don't get the key, you just get to know which key. You just get to know that it's the IA key, and you can get it via the IP command. Let me see if I can find it here. Here, I don't know if you can see this easily, but I can show it better. See, here. It's in the metadata of the DYD cache. So you know the diversity and the key are encoded in the higher bits of the pointer itself. So it's the location of the key, right? It's the location of the key? It's the logistic that stores the key? It's not a location, it's just which key. Because in ARM, you just have to call different instructions for the different key. So if you know that it's the IA key, you have to use the pack IA to sign it, or the out IA to verify it, right? You don't know anything else about the key.
Okay, thanks. More questions? We have time.
Well, it looks like...
Big applause then, big applause. Surprise, surprise, surprise. We have an extra talk from a new speaker. Hello, hello.
Venga, va.
Let's start.
So this presentation was supposed to be happening tomorrow, but as long as we have like half an hour, I will make it. It's a quick presentation on the Kai and show you some of the features that R2AI is including, which is the capability for decompiling with R2AI. So first of all, I would like to present myself. My name is Pancake, but other people knows me by Sergi. I work at NowSecure, which is a mobile security research company. We do applications and software for analyzing mobile applications for iOS and Android and improve the privacy situation on this field. I'm the actual author of Radare. You probably know me, so you come here to the conference. It's kind of a generic slide. And I'm a free software enthusiast, so I've been developing free software tools and contributing to the open source scene for a while. So this year, actually last year, was a huge boom on language models. There is a lot of projects trying to find real use cases for these technologies. So I started playing with Llama, which is one of the most popular implementations for language models to run them in local. And there is actually, every week there is new models, there is new commits, new features, adding support for larger context and new applications. So I wanted to play with that and integrate with R2. So I started building R2AI. At the beginning, the thing is that Llama is written in C++. There is a C interface exposed, but it's kind of like really messy and not very well maintained. And most of the people is basically relying on the Python interface. So it was the easiest way for start playing there. So at some point, we'll end up writing everything in C, so there will be any extra dependencies. But the thing is, right now, R2AI splits into different tools, and I will be showing one of them, which is the Kai. So first of all, I want you to understand that AI is actually something that you cannot rely like 100% with that. The output can be different, but depending on the model, the parameters that you use. Also, it can be giving you wrong answers, and this is something that is known as hallucinations. And as long as this can be dangerous or wrong, there is always the need for someone to verify the output. And I hope that you understand that sometimes the output doesn't need to be perfect, but it's so helpful for us, and we must use these technologies as a tool, not just as a replacement of people or other tools that are probably more reliable or trustable. But at the end, it will maybe solve and give us a lot of ideas that we can integrate with our workflow and solve the problems that we need. To install the tool, it's just r2pm-ci r2ai, but actually there is 4 different packages. R2AI is the command line tool. It's written in Python. It shows you like a prompt like in Python. And you can just load the model that you like. So it's able to download models from Hugging Face, but you can also provide the ones that you like, specifying the full file system path. There is R2AI plugin, which is basically the same thing, but implemented as a plugin for R2. So you have the R2AI command inside R2, and then you can make queries to the language model. You can pass the output of a command inside the language model, or make actually the model interact with R2 automatically. And you can make questions like, what's the password for this application? Or where is the encryption key for that specific algorithm? So it will be running the commands automatically and solving the problems for you. Tomorrow there will be a presentation for the auto mode, but I will be focusing on the Kai. And then there is R2AI server, which is a simple shell script that basically allows you to start different web servers. So R2AI is exposing an open API REST server, so you can actually make curl requests to this web server. And make it use like OpenAI, Claude, and any other backend that works in the same way. And finally, there is Decay, which is a simple JavaScript plugin for R2 that takes the Decay command from the command line and executes curl one-liners to the backends that you configure to get the response with the integration of the commands that you have in R2. This is the way that you can search for the package, that's the way that you install it. And let me explain what's Decay. The thing is that Decay was actually part of R2AI, but many people was wanting to use it or trying to integrate it or installing it, and there was some issues because the Python bindings are not well maintained. Actually, they fixed that like a month ago, but they were breaking the versions of the pip packages for a while. There was like some incompatibilities depending on the operating system because it depends on hardware drivers. Like you have NVIDIA, you need to install or build the dependencies for your own. So actually, the best way for not depending on all these issues was just to write everything as a standalone plugin for R2 in JavaScript, and then just use HTTP to communicate with the server. And then the server can be anything you like. Can be R2AI, can be Claude, can be OpenAI, can be whatever you like. So this was basically simplifying the problem of having 1 gigabyte with specific plugin built for your hardware with just a few kilobytes JavaScript file that runs and loads quick inside R2. As I said, at some point, this can be written in C. I wrote it in JavaScript because it was probably the easiest way for doing it and also the easiest way for experimenting with the plugin. So you can just load it at runtime. You can add new calls to curl. You can modify the behavior very easily. But there is nothing that blocks us to implement the same thing in C. So we can just make curl requests or make a communication channel with a Llama server or the Open API servers. So this is the things that you can do with Decay. Right now, Decay is able to communicate with Open API servers, like I said, Llama, R2AI, and so on. Then you can also use Hugging Face chat. You can use OpenAI and Claude endpoints. You can decompile into many languages. The thing is that a language model understands the context on how to translate from one construction to another one, not just from human language, but also programming languages. So you can have a function in C, and you can tell the language model to write it in Python, or write it in shell script, or in Haskell, and it will do it for you. The thing is that there is a lot of models, many of them that are open source, that are trained with open source code. And the language models are able to translate all these constructions from one language to another one and understand how to refactor this code to make it more optimal or clean or rename variables, change the strings, whatever you like. So you can basically use this as a way to decompile code. Decay is not taking assembly code because there is very few models trained with assembly code, and the thing is that as long as there are so many different assembly languages, it's better not to depend on that because this will require having the same thing implemented for every single architecture. And actually, one of the things that R2 is providing is a pseudocode that's basically taking the disassembly that you have into a pseudocode. So instead of having mob instruction like mob EAX, 33, you get EAX equals 33. So you have like a pseudo representation of the instructions. So you can basically provide this to Decay, and also you don't need to write all the control flow like if constructions, switch statements, loops, for, while, etc. Because you can just provide labels and gotos. And you can tell the language model to replace the labels and gotos into something that makes more sense for a high-level construction, like if, else, for, while, etc. And then when you get this decompilation, you can say, okay, I want to get this decompilation in Python, or I want to get this decompilation in Swift, or in C#. You can also use that for explaining what the function is doing, so you have like a long function, and maybe you don't know what's doing, or maybe you have a lot of functions, and you prefer to have like a quick explanation about what this function is doing. Maybe it's correct, maybe it's not, but most of the time we will give you a quick overview of what the function will be doing at some point. So even if it's not correct or it's not 100% exactly, it will help you a lot. You can also use the Kai for renaming functions, so it's able to understand what the strings that are referenced, also understand the functions that are calling, so it will be used for auto-naming functions. There is functionalities already implemented in R2, but using a language model gives you like much better output, because it's not just constructing a string from other output, it's also understanding that humans, when we code, we decide to give like meaningful names to the functions, not something that is constructed from what the function is calling. Also, it's able to do type propagation. It can also able to find and understand the size and type of local variables and arguments and return types. It's also able to find vulnerabilities, so you can give the compilation of the function that the same Kai has generated, and you can ask the language model what's the vulnerability, or there is any vulnerability in this code, and how to exploit it. And then it will give you the exploit or an approximation about how to start messing with the limitations of the buffer, if there is any vulnerable function call that is referenced from this function, like a string copy, things like that. And then you can also use combination. You can, maybe you just want to have the compile of one function, but the problem is that sometimes you just need to give some context to this function. So you can provide a bunch of functions, like maybe the function that you're calling, who is calling that, and the functions that are referenced from this one. So the language models understands the context and can give you better explanation about the function behavior and also the types for the type propagation and understanding of the vulnerabilities, and also can combine these multiple functions into a single one. And finally, it's using a seal for inferring and identifying all the function arguments, all the computed values, and things like that. I will show you a couple of examples for that. The first one is using, well, I will explain first how to use that. The command is the Kai, so you just, after installing the r2pm CI the Kai, you get the new the Kai command. And you can use -e for changing the configuration options. The same way that you use -e in R2 to change the options, you can use the same thing for the Kai. And the prompt that the Kai is using for the compiling is this one. So it's basically asking the model to show only code, don't explain anything, and then simplify the logic of the code, take the function arguments from the comments, rename and remove the assignments, refactor the goto into for if while, and use better names for variables. This prompt is something that you can change at any time. You can, this is the default one because I realized that this one works quite well for Claude, for OpenAI, but also for local models like Granite. And as you get the output from the Kai, but then you use the Kai -q to make a question. So you can basically extend the prompt with another question that will be extending or evolving the response from the language model. Like you get like the compilation, and then you make a question like, oh, this local variable, I wanted to rename it to something else. This is the most common options that you have. You have catch. It's basically using the annotation command for saving the output. It's also able to specify the language that you want the output in, like C, Python, Swift, whatever you like. And by default, it will be picking the output from PDC, which I said is the pseudo-compilation output from R2. But you can specify like a comma-separated list of commands. So you can also embed the output from r2ghidra or r2dec or any other command that you like. Like PDSF, for example, that will be enumerating all the strings that are embedded and the offsets of each of these strings. So the language model can understand that if there is any offset, it can be referenced or related to the string. And finally, you can use hlang to specify which is the human language that you want explanations in. So you can ask the language model to give an explanation in Catalan and in Japanese or the language you like, because, or put some comments inside this assembly, and convert this output into R2 comments and get the thing embedded inside R2. So demo time. We'll try to be quick. We're still in time. This is a simple, vulnerable program. It's a hello world program that takes one argument. And this argument is the second string that will be printed after hello. The thing is that you see that the second string is copied into a local variable that have like a fixed size, which is 32 bytes. And using the Kai, the output will be the one that you see in the right. As you see, is way better than something else that you will find out nowadays using r2ghidra or r2dec or PDC, for example. So the output is quite good. It's able to understand that the function is main, so it knows the return type, the arguments and the types. It knows the size of the local variable. It's inferring it directly from the set disassembly. And then it's also able to understand that the string is appended with a format string at the end. So I'm using the chi-q to make the question, is this code vulnerable? If so, explain and write an exploit for it and show the explanation and don't show me the code again. So this is the answer. So it says, yeah, this code is vulnerable. There is a buffer overflow. It takes the argument 1 and pass it to a string copy. And if it's longer than 52 bytes, it will overflow and buffer the write and potentially overwrite the adjacent memory, including the return address of the stack. So yeah, you can make extra questions to the language model. This is a very simple example, but it's this kind of vulnerabilities and other are also spottable by R2AI. But it all depends on the language model you use. I mean, depending who was trained, it will be giving you a better answer. If you like, I can make the same demo in live, so you will see how that thing works. I'm in the R2AI directory, but I will be jumping into the demo thing. So we have the source code. I'm compiling this simple program, opening it with R2, analyzing it. And yeah, you see that this is the function. It's a very simple function. And using PDG, which is the r2ghidra, the compiler, whoops, wait. Demo time. It had an async build because I was messing with a crash yesterday. So so I will show you the code meanwhile. So this is the implementation of the plugin. You can see that at the end is using the r2 plugin function to register a new core plugin. This core plugin is taking a string, which is every time that you run a command, it will be executing this function, and then it's calling the implementations. Here you have all the flags that you can use, all the configuration options, and the commands that are running behind the scene. Okay, so let's go back, analyze the thing. Now we have PDG. Come on. That's r2ghidra. Anyway, we have PDC, which is the output from the set compiler. This is what the Chi is taking as argument. And some of the things that have been improved in PDC is that it's taking the information from the calling convention, so it knows which register is used for return value, which ones are used as arguments, also the function name, also the types from the arguments in the function signature that you are using right now, but the Chi can extend and change that if it's needed. So, yes, at PDD, this is what it's used for r2dec. And just use the Chi. I will see the options, so I will depend on Claude for this example. And we'll do the compiling in C. We get this output. We can change the language into Haskell. or scheme. Okay, so as you can see, there is like so many things that you can do here. If you check for the help, you can use the -x to explain what the function is doing. And if we change the language, we'll be giving you the response, that language. So let's try to use the question thing and change the language back to English. Oops. Have the compilation. Oops. No. Yep. They was actually fixing the vulnerability in the response. So you get an explanation on where is the bug. So, as you can see, changing the prompt is something that can affect a lot the output, so it's important to try a lot of the questions that you can make to the model, and also that depends a lot on the model you're using. So I'm using Claude for here, but if I change that to OpenAI, for example, the output will be much different. So I can try that with API OpenAI, and we can decompile, and let's see what's the output. It's assuming that the local variable is called greeting. I can ask him to rename greeting variable into buffer. It should be doing that. Yep. Okay, so next demo, let's go into something more complex. I wrote a simple crack me for iOS, which is a function that just checks for the password. So this is the actual code in Swift, which is taking a string and returning a Boolean. And the output for PDC is all that stuff. So it's actually, you see that one line of Swift decompiles to quite a lot of code. But if you use the Kai, we can basically simplify all that stuff into just this, which is basically understanding, removing all the trash, all the things that doesn't really matter, and at the end is giving you a code which is much more easy for us to understand. And we can change the language, and we can tell, okay, I just want to get this decompilation thing in Python, or maybe I want to remove some unnecessary logic and get the output in just one line of Python, which is something quite easier for us to understand. And some fun thing, you can also use bash, so you can decompile into a bash script. And as I said, it's just the logic that the language model understands and can translate to whatever you like. If you try to decompile Swift using real decompilers, you will see that they will probably fail and give you an answer that is quite useless. So if you try IDA, Ghidra, binary engine, and so on, they will not even found the string. I will tell you why, and this is the reason is because still the strings in the short strings in Swift are constructed in assembly code. And as long as the constructed string is built in memory, filling some register values and calling the functions with the register pointers, it's not really spotted by all these tools. So there are some plugins for IDA and so on to spot that, and this is used also by Rust. It's not something Swift specific. But you can see that the output of this is quite useless. You don't even see the text of the password 123, which was the text. And if you check the code, you can see how the password is constructed in these instructions. Yeah, that's LLVM optimizations. And you will find these kind of optimizations more and more every day. So yeah, the thing is that using the /az command, it will emulate all the code, find all the computed strings in memory, add the command, and this command is then used by the Kai to infer the values from the register passed to the function call to the argument. Yep, that's it. So let's talk about the future. There is still a lot of things to do. One of the cool things is that you can use the Kai with different architectures. It's just not just ARM or Intel specific. I've been using that for STM8. There will be a presentation tomorrow showing how the Kai was used for the compiling a firmware on an 8-bit CPU that is not well supported on any other tool. The PDC can be still improved quite a lot to make the work easier. Also, there is like a lot of things that can be improved not just in the PDC output, but also in the Kai, improving the prompt, like making it different. And right now, the Kai is not able to interact with R2, so if there is some lack of details, you need to provide them manually. But the cool thing is that at some point we'll be able to make it automatically, that when the language models need some information, it will be able to execute commands in R2, get this data back, and improve the output automatically. This is something that is done by R2 AI. This will be presented tomorrow. But I think that things like that will be so helpful for everybody, and I just wanted you to know that you can try this out nowadays. And you don't need to use payment services like OpenAI or Claude. You can run all the stuff in local. Yeah, that's it. Any questions? Wait, microphone. Go.
Yes, so thank you for the talk. It's a simple question. So I think you are using, if you want to use it locally, you will need some models from Hugging Face or something like this.
Correct.
Are you planning to maybe do something to have your own models optimized from some stuff?
Yes. Actually, there's a couple of things. So I said, if you check in R2 AI, oops. Just run make, you will get into the shell. And using -m, we will show you the current model. Uppercase M will show you which are the recommended models that you can use. Just using -m and the name of the model will be downloading that from Hugging Face. You don't need to use the browser or anything for doing that automatically. But actually, we are doing this. We started to build a model that is fine-tuned with information from the book and also some extra data set that we are writing by hand. It's taking all this information from the R2 Fortune messages, the R2 documentation, the book, the configuration options, all the help from all the commands, the source code. At some point, maybe I will be helpful to take data from the chats that we can take like question answers from people, anonymizing everything, obviously, and all this data set is public and free. And the idea is that as long as all the models, or at least the commercial ones, are using the book and other data that is public right now, we want to get this documentation well written, because otherwise the models will giving you the wrong response. And we can also use this data set, and we're experimenting right now with different fine-tuning options for improving the output. So right now we have like a pretty small model that you can make questions and give you the command that you need to run in R2 to resolve the question.
I think you can even enrich with metadata that you can provide. So if you have keywords, for instance, or things that you want to get in order, you can also feed the model with this.
Yes.
And probably it's what you're mentioning right now. Yeah.
Yeah, awesome.
Thank you.
Thanks. You're welcome.
Any other question? So thank you, Pancake.
Offline. Thank you.
Okay, so now we have a break until 2 that we have the next talk. We have some food in the garden, so enjoy it and see you here too. Thank you.
Cuckoo, cuckoo. Sit down, R2 users. Come on, come on, come on, come on. Fast, 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 fast. R2 run. Come on. Super. Let's start with the next presentation that is titled Hack-Proof Your Mobile Apps. Are you ready?
I am.
Nice.
Let's go. Thank you. All right. Let's see if we get the slides. Siesta time, so I hope you don't get sleep. Have some stuff in place to prevent that. So let's get started. Let's boot the device first of all. And while we do this, I have some questions for all of you. How many of you are experienced in mobile app security? Of course you do. Okay, but not so many. That's good. How many have heard about the OWASP MAS project, Mobile Application Security, MASVS? Very good. I hope you still learn something today. How many use it regularly? A little bit, okay. Nice. How many has contributed to the Mobile Application Security project?
It's like that, you know?
It's in GitHub. Yeah, Pancake has. Okay. So let's change that. Loading, and let's go. So this is me, Carlos Olguera. I have here let's click on the two apps and come from OWASP. I lead the mobile application security project as OWASP, at OWASP, and also work at NowSecure, so yet another NowSecurian for the list. And you can find me in LinkedIn and as Carlos Olguera, and in Twitter, X, whatever, at grepharder. So let's get started. We're going to chat about, this is a bit of a mobile hacking 101. Let's start with the attack surface of an app, because if you want to protect your app, you need to know how to hack it first. And to do that in an organized way, if you don't have any idea, it is good to have some guidelines. So that's what we do in the OWASP project, is provide you guidelines and things that you can use and try to make this accessible for everyone. So the project is not only for beginners, but it's also for professionals. So this is a guide that when you're a professional, you will want to come back to it and follow all the steps and all the guidelines that we have in there. So for this, we have a very special app this day that we are going to download to our device, which is R2Talk. It's a possibly secure app. And and yeah, you can go, don't mind the German there, you can download it and get it to your device, and then you can extract it. Anything that I say in these slides, you can find in the MASTG, how to get an app that you shouldn't be able to get, how to install it, how to decompile it, all these things. So I'm skipping the explanations because then you can find it later there. So we're able to get the binary of the app. In this case, it's Android, so that's an APK. You just rename it to zip, unzip, and then you got the contents. There are many things inside. This is also explained in the guide. Android manifest, pictures, the code itself, and so on. So in here, just with this package, we can start looking at areas of interest. So let's see. There is an API key there. That should be bad, probably. One thing, the colors. You'll see the colors. They're all the same. They have a meaning. You will see that later. And they mean there is a category. So whenever you see the same color, the same tone is the same category. That will come later with some labels. So the next thing that we see is that after analyzing according to the guide, etc., we found a CVE on that second library over there. And also we can see that the app has obfuscation. All these things, apart from the CVE and the hardcoded API keys, they're not necessarily good or bad things. There are things that we are seeing in the app, and they they maybe have a meaning that you can use to hack it, or to know that it's secure as expected. So let's now run the app. So, boom, it cannot run. There is it detects root apparently, so, and I'm using a rooted device. So what do we do when we see this and detect root? They have an app and detect root. What do we do? Cry. Let's Frida it away. Boom. Okay, now we can continue. So let's see what is in here. A login page, you can use biometrics, etc. So there are more stuff that we can analyze here. It uses OAuth for authentication, a new category, authentication. It uses TLS version 1.3, that's good, and talks to the R2talk backend in the cloud. We see it also offers user authentication with biometrics. And now we open the app. So I don't know if you can read the conversation. It's very interesting. Hey girl, you go into the r2con, not sure yet. You'll have to convince me. I heard pancake's gonna be there. And the rest, you know, radar. So we see chat messages. They should be stored somewhere, right? The app encrypts the messages. That's good. Another question is how it encrypts those messages. Might be poorly done. So you see there, it encrypts and stores in external storage. That doesn't sound very good. What else? You can send pictures of pancakes and cats. So these are also saved in external storage. This one is probably fine, but maybe other pictures more compromising, you know, that's maybe not a good idea. And it also allows you to share these pictures with other apps. So for instance, your own cloud, whatever, boom, then it's going to be there. So that's another potential attack vector we could use if it's not properly done. So you see a lot of X's there. We have many instances of all these different categories there. But there's many more to this, like there's thousands, hundreds of different weaknesses that we can find in mobile apps. But we can all put all of them in these buckets. So if you look at what I'm going to present, all the weaknesses, and you find something that is not on those buckets, let me know, I'll give you a prize. Because those buckets were specifically designed to contain all possible weaknesses. So what are, oh, I forgot, it uses the camera, also privacy, very important. Probably the mic and other things, right? So that shouldn't be a vulnerability, but a weakness is not necessarily a vulnerability. It can be something else that is bad because of GDPR regulation, right? So those colors, this is what I mean. So this is the attack surface of the app. You can attack the storage. You can abuse the crypto, maybe. Authentication, network, the interaction with the platform being the Android system or the iOS system. Then code quality, like, you know, buffer overflows and other stuff. Resilience against reverse engineering and tampering, Radare, Frida, etc. And privacy. Privacy is the latest one that we added, I think last year, not this year, because it's very important and it wasn't covered before. So this is a standard. It's called the MASVS. This is the highest level of everything. It presents these categories and some very simple controls, like storage. You should store the app data securely. Crypto, following security best practices, like crypto best practices and so on. So the requirements that it presents are very simple and very high level, but they get refined later in what you see here, the MASWE, which is the weaknesses enumeration. If you know CWE, which probably many of you do, this is it follows the same concept, so to say, describing weaknesses at a higher level, but not as high as the MASVS. So this gets a bit more specific. And then we have the MASTG. The MASTG is explaining all those things that I told you before, like how to unzip the app and get into it and find all these things. And there are many techniques and there are many tools that you can use. And it has, of course, many test cases. So you have kind of like a checklist of things that you know if you do those things, you're going to find a lot of vulnerabilities or weaknesses and things that represent some kind of risk in the mobile app. So this is to illustrate that a little bit. So we go from the highest level, very abstract and very general. It's not even about Android or iOS specifically. Something like insecure crypto is bad, to the weaknesses, which speaks to one specific thing, like weak crypto algorithms are bad, and the app uses those. And then we get to the MASTG, the testing guide, where you get to the hacking. You get your hands dirty and you go and test for these things. Specifically, you will search for cipher objects in Android that use the weak DES algorithms, for instance. So this is another view of the same thing. So you can see that there is even more. We start with a control from the MASVS. It's about using current strong cryptography and industry best practices, very abstract and general, but that's intentional. And then we have a specific weakness related to best practices in cryptography, which is about random numbers generators that should be cryptographically secure, right? And then for that topic, we have many tests. One being searching for insecure random APIs, like this can be the random API in Java, for instance, but also looking for non-random sources, like developers sometimes think that you can just or you can just use the time from the machine as a random or some weird stuff. So we're going to look for that as well. And the cool thing, you'll see I'm very excited about this thing later, is the demos. Not demos in sense of conference and presentation demo, but we have actual demos with sample code and the test scripts. So this is like, we're going to take those tests, we're going to apply to a real app. So you can learn how this works. And do it yourself as well, you will see. So this is everything in our website, masobas.org, and it's also in GitHub. So we have the MASTG repo, MASVS repos, everything is in GitHub, and you can contribute, and it's really nice. This is the website that gets built out of all these repos and documents. And here you can see the weaknesses. The weaknesses are the newest one. They're still in development, so the MASVS is there for many, many years, but the weaknesses are very new. And they are like a refined version of those controls, as I explained before. If you go to the website, you see the full list of the current weaknesses with IDs, titles, the platform they belong to, the MASVS IDs, profiles. That's what you see there as L1, L2 is like maybe you have an app that doesn't care about jailbreak or root detection and these advanced threats. So you would just apply L1, it's very basic security protection. Or if you have like a banking app, financial, you will use L2. If you have a gaming app, you would use a resilience profile as well. So this is like you are tweaking according to the threat model of your app, and then you will select the weaknesses that you need to test for. This is the page of a weakness. It's very small. I know it's not intended for reading, but it explains what is bad in an overview, what can happen if the app has this weakness, what is the impact, how can this happen? Like, how can a developer introduce this weakness into a mobile app? How to fix it, of course. And it has the links to tests. So you can navigate from weakness to test, to demos, and so on, as you will see. If you navigate to a test, the test is going to explain first why we are testing for this, like specifically for one example, because, why we are testing for this, because the weakness is general. It applies both Android and iOS and explains important concepts. But here in the test, this is a test for Android or for iOS. It's going to talk about the specific APIs that you need to select, the specific features that exist in iOS and Android. So this is much more specific, and then it gives you steps that you can follow, 1, 2, 3, and then you will get an output. That's called the observation. And then in the end, explains how to evaluate and get an answer. Is the app vulnerable to this or not? And then it has some links to demos. And the demos are going to be, okay, let's get this test, let's get an app and run the test on an app, and that's the demo. We're going to explain everything in detail, why this app specifically has this, this weakness. So for building all these demos, we needed some apps that are, let's say, reliable and simple enough also. And the idea was to contain that weakness in an app that has nothing else but that weakness. For learning purposes, this is great, because if you want to reverse engineer, you won't be distracted by other things going on in the package, in the binary. And also, I think it helps you if in some situations you need to test for something very specific on a very specific Android version. For instance, testing things like on iOS, ATS configurations, on Android, the network security configurations, clear text enabled or not, and this version, if you have this parameter, if you have this min SDK, whatever, so it can be very complex. If you have an example like this that you can just take and play with it, as you will see now, that is so much better. So I created these two apps, one for Android, one for iOS. Intentionally, like the UI is, I try my best to make it look exactly the same. And it's very simple. It has a UI file and the code, and always the same function that is called mrmacete test. So this way, we can always, if you open the website and you go to one of these demos, you can copy, paste to the clone repo of the app, and it must work. So we are going to do right now, so you believe me. So this is, let's use this one here. Oh, I'm starting with, if you just clone the repo, this is what you get. This is the function. You can make it a bit bigger. If we run this, you see it is extremely simple. If you click the start button, it's going to run exactly this function. And it's going to return some text, so you can read something and see that something's going on, right? But that's it, very simple. Okay. Now we go to the website, we go to a demo. Sorry for the scrolling. And we can get the original code from here, copy to clipboard. Select all, paste, save, and run. So this is tested continuously by humans so that it works, but also in the GitHub Actions. For iOS, not yet in the GitHub Actions, but for Android, we are already building the APKs in the pipelines. And also in the future, we're going to run against virtual devices, so to ensure that this is continuously working. So let's go back to the presentation. So that's how you run demos. And let's go into the demos. So this is the first one. We just saw it. This is about an RSA private key that is hard-coded. So let's take a look here. This is the demo. And I'm going to actually open the test first so you can see what's in the test. And then the demo is like, it's like an instance of the test. So in here we can see typically the apps would use the security framework with specifically this function, or Common Crypto with this function, or CryptoKit. So there are many possibilities. Then we have steps. This one is very simple. Why is that simple? Because we contain all the information. It is called a technique somewhere else, so you can learn about doing this stuff with Radare. We don't have to explain again and again in every test. And then after doing this, you should see all the instances where this thing is happening. And then the test is going to fail if you can find these calls to these cryptographic functions. that are receiving a hard-coded key. So let's take a look at the demo. In the demo, we have a sample code. I'm not going to show you. I'm going to keep to the disassembly because that's what we are going to use. I'm going to show you in the end. But you see there's a very long code here. So let me get to the text again before, at the end. Very big function, right? So you will unzip the app, you will open it, you will get the binary, and then you can use Radare with the I version because we are, option, because we are gonna load this script. This script is specifically prepared to do this. In the future, we might move it to Python to make it more dynamic and not have to hard code all these addresses and so on. But we're starting with this very simple. So we're gonna first search for the uses of specifically what was mentioned in the test. This is a demo that is specifically for this. We have another demo for Common Crypto, and we might have a demo for Common Crypto but with another tool, so we can have all these combinations, so you can also learn to do the same thing with different tools. And then we search for the cross-references, and then we're gonna just print the function to a file, and we also could find the key, the hard-coded key, so we are gonna also store that. And then we have a script that you can run, and then it will get you all the output. What is the output? It's also here. You can see this is the output. We could find a use of that function. We can search for the cross-reference. Where is this function being used? In this other function. And then we have the full code above. And then it is telling you, I'm going to hide this intentionally, the test fails because in the end we can find the key, which is here, and we can see it with Radare at the end. So let's, now I'm going to show you. It's gone? Oh no, it's working. So I said this is all in GitHub. Every demo is containing a folder, so you can just clone the repo, go to the demo, open the folder, and in this case you can find the app binary. So we extracted that already from the IPA, so you just have the main binary of the app to make things easier. And then you have the original code, which is here, and the rest, the test script and everything. So, and also the cool thing is that if you just open here in integrated terminal, you should be able always to run the scripts, and that's going to override these files in this case. That's why you do see anything meaningful here. The cool thing with this is then you can take the R2 script that is, what is it gone? Here, sorry. Here, and you can change it and play with it and try to get other inputs and so on. You can try with another binary. If you replace this binary with another one, you can try to do the same and play with this. So going back to the code, this is the disassembled code. So what we can do is, I'm going to show it to you here. So this is the function. And let me just check again here. We were looking for this, right? So we go to the function. And then we see that it's been used here, but we cannot really see where the key is coming from. It has to be there somewhere, but we cannot see it that easily. So in this case, you could spend some time analyzing all this disassembly until you find the key. Or maybe we can use AI and give this and then get something out. So that's also here. Decompiled, I use the O1 review model, and this is what we get. You can see the key bytes shortened for brevity, and then you can see how specifically all this code is being used. I'm going to show you now so you can see what was the original code and what is the new code, the AI decompiled code. So the original code, we have it here, and then I'm going to open the other one here to the side. I'm going to hide this, I'm going to hide that, and I'm going to collapse this, and I'm going to collapse this. So you can see more or less. The function doesn't have the same name, but that doesn't matter. So you can see that it's basically the same, more or less, right? So good enough for me to understand what's going on. It even translates all these things. Interesting. It's breaking. And it explains you without telling it to explain, like, look, step 4, step 5, and so on. Really nice. Let's take a look at a second one. So this is this one. This time, common crypto and insecure encryption algorithms. So the second one is this test. In this case, for insecure encryption algorithms, we have to take a look at common crypto and CryptoKit, and not the security framework in this case. That's explained over there. And there are several algorithms that we might be able to find there in both cases. And then we're going to run the same way with Radare and a similar script. And we'll get the observation and the evaluation, and we're going to see that it contains some of these algorithms. So this is the demo. Again, the disassembly. This is, I think it was a bit shorter, but still, see, we can already see the cccrypt function here. And then we can guess that here probably we can find if this is encrypting or decrypting, but we don't know. So let's continue, and let's see if we run all these commands. They are very similar to the ones before. Let's search for uses. Let's cross-reference, find cross-references. Let's go there. Let's get that code, and so on. And this is what we get. Again, it's that piece of code, again, but we still don't know what's going on. So we need to keep researching. So we do that, and we find out, okay, if we go to the headers of the function, we can find what are the arguments and what they mean. So for instance, we have first operation, it's encrypt or decrypt. Then we have algorithm. We should be able to find the algorithm over there. Then the key length, data in, data out, blah, blah, blah. Okay, so we do that. Then we also find what is the meaning, what are the numbers that we can expect there. 0, 1, like AES is 0, DES is 1, triple DES is 2, and so on. Same with the algorithms and the mode. Encrypt is 0, decrypt is 1. So then we go back, and then we try to comment these things. So you see, okay, it's 0, so it's encrypting. It's 2, so it's triple DES, and so on. And then we do all this work, and in the end we can say, okay, so this is using triple DES, so this is vulnerable. Good. Let's use AI instead. So we did all this work, but actually, you know, if we would have used AI, we would have seen this thing here. We even see the key, we see the encryption, the text that is going to be encrypted. And look at this. You can already see that it's encrypting with triple DES, some padding, and you can see everything in there nicely. We're going to do exactly the same, so you see the before and after. And that was demo 18, which is this one. And then we're going to open here the original code, which is this. And here we're going to open the reverse code. Yeah, so original code, reverse code, and there you go. If you see, I'm going to scroll here so you can see more of the operation. So again, it's basically the same or good enough that you can understand what's going on in there and directly see all these things, which is, in this case, is exactly the same in that area of code. So it's really, really nice. So it's really good that Pancake did the talk before, because he explained all what can go wrong and how to make it better, so I don't have to. But yeah, I did it for several demos, so not every demo has the AI reversed code for now. We will add that in the future. But it will depend on the situation, as Pancake was explaining. And For instance, I think this one or the other one, it took me just 1 try, and in other ones, 2, 3 tries. It depends. But I use a very simple prompt in this case, and it worked pretty nicely. But I think because of the model, because this model can think, so it took more time to go through that. All right, and I think we still have a bit of time, right? One more demo. The last demo, which is about storage. Again, on iOS, the apps can try to exclude something from a backup, and this can be a good thing if it really happens. But if you read the guide, we tell you that actually maybe it doesn't happen, because even if you would expect excluded from backup, it would exclude something from the backup, but it doesn't. So Apple writes that in the documentation, like, yeah, you can use this function, but actually it's like it does nothing, but you can use it. You intend to exclude it, which is funny. So that one is here. So here is where we are explaining that. This is why this is so valuable. You don't have to go and find this in the Apple documents, because we do that for you. And hopefully when you contribute, you will do that for other people. But here you can find all that information. And then we're gonna, again, do exactly the same in the demo, follow the same steps. And we end up with, you see again, a very long code. So this time I'm gonna just go and show you the decompiled version. Basically, it's not working. You can see that the file is created here. It gets an API key, and then writes the API key in the file, and then it marks that file as is excluded from backup. So then we explain what you actually should do is probably encrypt that file. If it's very important, just prefer to encrypt it and not rely on this flag in the end. So this is again all the code and the results. You can see that we can find that string, then we search for where the string is used, so we can see in the disassembly this as well, not just using AI. You should still try to learn the reverse engineering, not just rely on AI, please. But yeah, the combination of you being able to reverse engineer and having AI, of course, is very powerful. So, but please keep learning and using Radare. So yeah, this is it for this demo. You can find Frida demos, of course. We have man-in-the-middle proxy for when you have some network stuff going on. All the things I presented with all those colors, you will find all the weaknesses, all the demos, and this is growing now with time. This is also, the demos are very new. Before we had like, the MSTG is a book. It's like, it was these phone books. It's really thick if you print it. So you don't want to print it, probably. That's why we build the website, so you can search for everything in the website and play with it and clone it with GitHub and so on. So please do that, and I hope you learn a lot. If you want to contribute, it doesn't matter the level. If you're a beginner, you're going to learn. If you're a professional, please contribute as well, because we need a lot of help to keep with this. And you can just, if you want to see a typo, you can start with that. Just edit, click, fix it, send it. That's something already. So we hope we can hook you with that. And yeah, again, this is me. And go to the website, contact me if you have questions or you want to contribute, especially. So yeah, thank you very much. Any questions?
Questions. One question, one book of Radare, free of charge.
Yes.
That question doesn't count for the. Come on, that's bullshit. Come on.
Yeah, if you go to the website, you go to the MSTG, and you see kind of all the components that we have, techniques, demos, tools, and instance. For instance, here, you see we have R2 Frida there. So we treat everything as a component, like a function, tools, techniques, and that's cross-reference across the guide, so you can always find all this stuff.
Let me reply, Novella. Read the fucking manual.
Read the fucking MSTG, yeah. Thank you. More questions? Well, I'll be around, so approach me anytime.
Big applause, big applause.
Thank you.
So,
Hello, hello.
Hello.
Welcome, welcome.
Thank you.
Are you ready?
I'm always ready.
Let's go with the next talk by Lars. Reversive fast and together. Let's see, okay. Big applause.
Thank you. Thank you. So hi, I'm Lars. And many years ago, I used to work as a reverse engineer for the Norwegian CERT. And I remember it was very stressful. So they would tell me Norway is under attack, and you have to reverse engineer this binary. So I remember like going into panic mode and sitting single-stepping through Ole debug like a crazy person. And my process was very like manual at the time, and I would say a little bit chaotic. And then in 2009, I joined a Norwegian antivirus company, famous for creating the first ever malware sandbox. And the guy who wrote this actually started his work all the way back in like the late 1990s. So I was working on the part of the antivirus stack that removed malware once we detected something. And that's how I kind of got into rootkits. Because the most difficult malware to remove is kind of the rootkits. So I did rootkit detection for a while, and I did some anti-rootkit technology for like the on-demand scanner, so it could detect hidden files. And then when we did the second generation of the malware sandbox, I ended up writing rootkits. So why would you write rootkits? Are you not working for a serious company? And the thing is, malware sandboxes are quite effective at detecting and analyzing files. So therefore, the malware authors typically try to evade us. And they do that typically by looking for signs of something that differs between like a sandbox environment and the real environment. So my approach was to create like a rootkit to basically hide our components on the system to kind of trick the malware into running. And I learned after like working with malware technology or sandbox technology for like 20 years that this is a very difficult problem. And if you've studied computer science, you might have heard about computability theory. More specifically, about the halting problem. So the halting problem is something like this. Given a description of a program and input, decide if it finishes or runs forever. And this is kind of a simple yes or no answer. And then there's this guy, Alan Turing, maybe you heard of him, proved that a general algorithm for all possible program input pairs cannot exist. This was proven in 1936, so it's a long time ago, before the internet. And furthermore, the halting problem is what we call undecidable, which means it's like super hard and impossible to create like a generic algorithm to solve it. Now I'm going to argue that the sandbox evasion problem is likely a variation of the halting problem. And I'm going to do this, I figured since we were in a university, I was trying to make something like super academic. So I have this very academic approach, where I'm trying to basically transform the halting problem into the sandbox evasion problem. So we start with the first part of the halting problem, given a description of a program and input. This could be translated into given a binary file, because basically the binary file we can decompile, and that can be sort of our description of the program. And we don't really know the input, for the most part. And then the last part of the halting problem could be decide if it finishes or runs forever, could be transformed into decide if it terminates early or runs intended behavior. So it doesn't need to be like this, but very often the malware will kind of check if it's running in some type of sandbox, and then very often it will just terminate, or at least avoid doing whatever like malicious behavior it intends, so that we don't detect it. That's like the gist of it. So this would probably mean that the sandbox evasion problem is likely also undecidable. Super academically proven. The thing is, for this project, I was interviewing some malware and threat analysts that work for various cybersecurity companies. Since it's been a long time since I actually did this as my day job myself. I'm kind of understanding a little bit about how they approach reverse engineering, what their workflows were, and like what their pain points were. And it turns out that most of them relied on sandboxes in some way or another. They see a lot of files, and so it's very easy to kind of use this, some type of sandbox for like an initial analysis. The challenge is that very often they don't get the results they want. So there's some infinite many reasons why some program wouldn't run in a sandbox. So very often they just don't produce any information. And if they don't produce any information, then they tell me that kind of manually reverse engineering is slow, which well, at least it's slow for me as well, so I understand. It can easily take them a few weeks just to analyze a single file if it's like some type of a little bit complicated. And then also we have like lots of like false positives and false negatives, and just in general too many files to worry about. So that's kind of the challenge. So I'm asking the question, can we make reverse engineering easier and faster? So I came up with this idea of, let's call it a reverse engineering paradigm that I call iterative reverse engineering. So in this way of reverse engineering, you will basically start with doing a quick static analysis. So you look at like the strings, what type of file it is. I want normally just to get all of the disassembly and the decompiled code so I can kind of scroll through it, just to have an idea. This is basically how I used to work as well when people would send me files complaining that the sandbox didn't work. They would tell me, your sandbox is bad. This malware doesn't run. So it's kind of like I like to see what code it is before I make up my opinion on how it should be running. So then you use this information that you retrieve from your static analysis to basically tweak your dynamic analysis. This means that if you can study the file to a level that you can maybe recognize that it requires some command line parameters. Maybe you can see like what type of file, at least you know if like a 32-bit file or 64-bit file, it will tell you something about the environment in which it should run. So then you run the sample and then take output from the dynamic analysis and use that to kind of refine your static analysis. So typically, like in a sandbox, you can kind of get this with events, which would be typically like API calls, API like parameters and stuff, and some traces, which should tell you like what type or what code has been run. So you can kind of recognize that if it's terminating early, you can kind of understand maybe where it stopped. So that now can become your like a focus point of how you can force the malware or force something to go down a different branch. And as you kind of make new discoveries, you kind of just iterate on this until you have the required result. So it's very rare that you need to like totally reverse engineer every single bit in a file, because that will take a very long time. So hopefully you should have some type of idea of what you want to figure out. Someone's probably asking you some questions about this file. Is it suspicious? What is it? What is it not? So you kind of just iterate until you have the answer you need. So this is kind of my amazing illustration. You start with some type of static analysis, and this will tell you kind of how you should tweak the setting for your dynamic analysis. And then you use the events and traces that come out of dynamic analysis to kind of refine your static analysis. This means that basically you should be able to kind of rename your functions and stuff based on dynamic analysis to kind of help you understand what different functions do and so on. So I'm making a web application to try to enable this. And it should come as no surprise, since you are in r2con, that the static analysis is based on R2. And it's basically we want to, as I told you, I like to just read the code starting from the entry point as my first step. And I've experimented a little bit back and forth, and I want to have like a UI where I get all of the disassembled code so I can kind of scroll through it. Maybe later we can add some filtering and stuff, but essentially I want to disassemble and decompile all code. And I also talked with some people who know something about UX. This is the first time I ever did a UI in my life, I think. I think this is my third iteration of trying to build like a like a web UI that makes sense and looks decent-ish. But the thing is, like, the good UX kind of boils down to responding fast. That's what they tell me. So it means that the opposite of good UX, like bad UX, is something that if you click something and that it takes forever to respond. So maybe it's like just it's annoying spinner and things like this. This will annoy the user. Whereas if you can make something fast, that means the user will be happy. And also it means that they can reverse engineer faster. And we know that disassembly and decompilation is basically CPU-bound processes. It means that for the most part, the CPU should be the bottleneck for how fast we could do it. So I'm trying to look into basically how we could use multi-threading to speed up, or something akin to that, to speed up the process. The challenge now is that R2 is single-threaded. So I have some ideas in this space. Basically, I rewrote the backend lately to use async Rust. So I have some ideas I might want to experiment with. But for now, at least, I'm just basically trying to split the work of R2 does into multiple processes. So auto-analysis isn't really, I didn't find like a nice way to split it out yet. So now we kind of do auto-analysis single-threaded, but then I try to do as little analysis as possible. And the requirement is you kind of need to get decompilation working. So essentially it means, in our case, that whatever R2 Ghidra needs, we need to kind of just do those steps in the analysis. And then I'm running like a subset of the analysis commands that normally runs during auto-analysis. I mean, R2 is kind of logical, so if you go into like the AAA command, you're going to see like the various sub-commands that it normally does. And there's lots of different ways that it can do auto-analysis. The most important operation is AAC, which is basically like a flat disassembly of the file and looking for call instructions. And the idea is if you find a call, then probably it's a function. These other functions I normally used to, this is like the most helpful command in R2 that Pancake ever showed me. So if you ever worry about anything like what a specific command does, or if you want to find some commands, then you can use this interactive help command. This is the best command. Okay, so once auto-analysis is completed in like a single thread, I save some meta information that I want to use later. So kind of wanting to branch out in multiple processes. I had a look at the project code to see how that was done there. So currently I'm using these commands to, the first one, AFL, will generate the list of all functions. And then I dump all of the flags. And then I dump all of the cross-references. At least for now, this seems to be sufficient. So I kind of basically just put all those R2 commands in a file. And then each of the multiple processes that will run later will basically just load the meta information into new processes. And basically, that's the way we can run things in parallel. So for now, I'll just do basically disassembly in one process and decompilation in another process, which is okay for like smaller binaries, but I was looking into finding some demo for this conference. I was looking at like some Go binaries, for instance, that statically link the runtime. So they become like 3 GB files. And in those cases, it takes a long time to kind of just go through and decompile everything. Another thing I want to point out is that with our approach, we constantly need to rebase the binary. Because I want to kind of compare the sample with whatever is information I get from dynamic analysis, and do that over and over again. And it means that every time the sample is loaded, it will likely load at a new base address. So rebasing needs to kind of happen automatically, because it's some of the most really annoying things. I know if I need to do this in my head, then I always get it wrong. I get kind of confused myself. So that's kind of a thing I might want to look into later. I didn't find like an easy way to do this yet in R2, so currently we actually just reanalyze the binary each time it's loaded at a new address. So this is one of the very many things I need to find a better solution on at some point. And then to generate events, we use Frida. Like lots of other people. So we use Frida to basically hook APIs. I like Frida because it's so flexible. And so just hook APIs, output the fact that they are called and which parameters they take. And then I also use the stalker module to generate traces, to get me like an idea of what code has been run. So the backend is written in Rust, so we just use the C API, the SDK, directly, and then I'm running a Frida server in the virtual machine. And then I enable this hypervisor debugging thing that I've presented on before, which basically it's running on the host in the form of an R2 debug plugin, and it has like access to the physical memory of the virtual machine, and it controls the CPU essentially via the GDB stub in QEMU. So this means we can single step anything, we can basically debug anything inside the VM. And it also enables something, a small little feature that I kind of wanted, which I call automatic load phase analysis. So the thing is that very often, if you drop a sample into a sandbox and it doesn't run, very often it's not because it's evading, it's because it's like missing a DLL, or it might be corrupted, and things like this. So what I do is basically, as I'm using Frida inside the VM to load the file, I essentially also connect my debugger and then just place a breakpoint on the entry point and then let it go. And if it hits the entry point, at least I know it's starting execution from the entry point. So I can kind of rule out if there's any issues that happen during loading. And as I said, it also enables us to basically do interactive debugging. I still haven't completed like the web UI for this. So currently, I'm running like a terminal thing in the browser, and just run R2 directly, which I will show you in a second. Oh no! So let's have a look what we are doing. So I prepared like a few quick demos of how this looks today. So just going to start by uploading a file, my passion.exe, and then it creates like a new analysis for me. And you can see right now over here, it's decompiling it. That means that auto-analysis has completed, and we also have already gotten all of the disassembly. So you can, as this is happening, you can kind of just browse through the disassembly of like the entire file. And now you can see decompilation is also completed. This is kind of what I want to do sometimes. It's kind of just scroll through things. There's like some strings and stuff might be interesting to look at. Imports from various DLLs. I mean, I do have like an R2 terminal here using X term, so you can kind of drop into an R2 shell. And then one thing I kind of find interesting is what I'm playing with is I have this like dual mode thing that I'm playing around with. Because this is from when I'm actually writing code myself. I always have this split screen concept. So I typically look at some code I've written before or someone else has written on the right, and then I type my code on the left. So I'll try to, and then with this, so, oh. Yes, no problem. For me, it's like if I'm looking at obfuscated code, then typically I prefer to read the disassembly. And if I'm looking at something that is nicer, then typically it's faster to look at the decompile code. So what I'm doing here is basically I'm storing the virtual address inside. This is a Monaco editor, by the way. It's amazing. What happened to Microsoft? All of a sudden, they become this really cool company that releases open source. And so basically, this enables you to kind of scroll down on the decompiled code, and you see like the corresponding assembly at the same time. They're basically synced up based on addresses, which I think is interesting. And then we can basically just start this VM. Since we kind of did our quick static analysis, we know it's like a 64-bit executable. This will boot up a VM. And eventually we'll see some whatever event Frida gives us here. So you can see it's loading the program. It's loaded our Frida script, and then it's telling me it's running from the entry point. Maybe that's too small for you to see. Did I screw something up? Oh, here we go. Something's lagging. And then yeah, basically you can see at least it started running from the entry point, and then it terminated. So not a lot going on yet. So this would be the situation where you didn't really get any events out. This is quite a very simple example. The idea is that you can kind of quickly look at the decompiled code and figure out that in this case it has like an if statement. Param1 is 2. And you can understand that this is it's basically a command line program. So it just checks if argc is 2 or not. And then there's a return down here. So basically means we need to give it some argument. So we do that, kind of tweak our dynamic analysis, and then run this again. And then something else happened. It logged me out. How rude. And we see now there's actually some more events reported to us from Frida. So we can see that there's a call to exit Windows, EX, which is obviously why it logged me out. Actually, 2 calls to exit Windows, just to be safe. So this means, okay, we have actually, at least we have gotten further into like this execution. So if I'm lazy now, I can kind of just run a different Frida script and just enable some tracing. So in this case, I just wrote like a special trace script to start tracing from main. Just to make the demo a little easier. So we select that and kind of load it again. And then logs it out again. So same behavior as last time, which is to be expected. And now we have some more traces from the Stalker module. So we see like the same two API calls. And now we can kind of compare the traces from Frida with the sample. So kind of side by side, and then syncing the views. I can kind of, so if you look at, I'm just going to scroll down on the left side, and you can kind of follow the code flow on the right side. You can kind of see what's going on. So it's going into this if, and it's actually executing the if. And then there's another if. And then it's calling this function at something 1010. And that is the thing that is calling exit windows. So probably this is not the function we want to call. So you're going to check this if. And it's checking param2 plus 8, which is the first command line parameter. And it requires like the first character of this, essentially, to be 0. ASCII 0. OK. So then you know that. You kind of go back and change the argument to be 0. Run it again with the same tracing. OK, so it's still signing me out. But now, doing the same approach, we can kind of see that this was no longer taken. And instead, it's coming to this next if. And so you can see like, OK, so it's doing whatever this madness is, and it's running this else thing, which again ends up in exit windows EX. But this is kind of like how I imagine you can kind of just iterate on it and tweak things as you go, and write your customized Frida script for the specific sample and kind of to speed up things. So I wanted to show you just quickly one more demo to just show you how this hypervisor debugger looks. So let's, I can just upload it again. So let's upload a new demo file. So again, it's doing analysis. This file was like shorter or smaller. So it gives me access to all the decompiled code quite fast. Start this VM and let it boot up. And then while it's booting up, we can have a look. Things. Sometimes I don't even know what I'm looking for when I'm doing this. It's kind of like, I'd still like to look at it to see if it's something I recognize, or I get like an idea of what it might be, or maybe, and what it's definitely not. In this case, I have like a Yara rule also, but sometimes can be helpful if you just to recognize aspect of code you've seen before. So I have like a Yara integration. And you can see there are some funny things, funny strings in here. So there's at least there's something to expect. Okay, so this program is running now, and it's Obi-Wan Keynote telling us the forces. Okay, that's interesting. So let's see. I'm a little bit confused now. I don't really know what I'm looking at. Is it? I mean, maybe this was not like the behavior I was expecting. So I'll run it again with. Let's do this tracing with Frida, just to kind of do the same thing again with enabling Frida tracing. Let this go. Just yep. And this time, the idea is that I'm going to use Frida tracing to kind of help me locate interesting code and kind of give me some hints at where I should look. Okay, so the same experience, it says the forces. And now we have like a lot more traces this time. It's actually tracing all the way from the entry point. And then kind of just scroll down and you can see, okay, all of this code was executed. And then eventually we get here. And so this, I'm missing a few events now, but basically it gives me an idea of where in the code how far it ran. So now maybe this now can become the code I want to look at. And if I read this code, it's basically calling get computer name, which is used to, in this case, it's used to get the Windows domain, and then it's checking for like if this is like it's the bank.com domain, and then there's like an if-else after. But you get the idea. It's basically maybe some malware wanted to only run on like a specific domain or something. So I figured I should show you just basically using the debugger to kind of just force this else branch, which is like a different approach. Obviously, we could use Frida and just fake the results as well. So you kind of have multiple options. So if you look at the assembly, and then basically it's a call get computer name, and it's checking for errors, and then yep, there is a string compare, and then it's testing the result of the string compare here, and then this is the if-else essentially. So if I go back and then iterate again, this time I will use my hypervisor debugger to basically freeze the VM on the entry point. So run it again, and then I do my thing in the beginning to make sure it's exactly the same kind of process as we did to make sure that the entry point is running. This time I'm just not continuing after. So this means that now it's frozen. Should be. And then it's giving me the option of using this debugger. This is how the UI looks for now. I'm still kind of using a Monaco editor for everything. But this information is retrieved via the debugger, so it's basically carved out from the outside, which means you can see all of the processes that runs on the system. And then you can see kind of all of the threads for each process. Like the memory modules for each process. So you can see movie exe is loaded Frida to improve it. Like the memory maps, and then also you can see things like all of the drivers and stuff. And then I have this R2 debugger terminal that enables me to kind of interact with it. So if we seek to rip, we are now at the entry point. And then from this analysis, I located this, basically the string compare. So I'm just going to go in here and just copy the virtual address of this instruction. And then place a breakpoint on that address. And let it run. It should hit, but something's wrong. No. Maybe that's, maybe I forgot that. Okay. That's true. It should. It still works with Soccer. It should. I think that maybe. Okay. Let's try it again. Maybe I did something wrong. That's true. You can disable Frida, I suppose, but I'm not sure if it should matter. Okay. Let's see. Try it again. Yeah, I think there were some issues. I was running this demo in my hotel room, and there was some tricky things. Stressed me out a bit, but this is it's fine. Let's try again. See if we can make it work. Okay. Okay, so we're at the entry point. Connect R2. Get this address. Seek to it. Place a breakpoint. And now it worked at least. So the breakpoint is hit. In this case, I just want to just force the else branch just to show you that it's like displaying a different message box. So you can see rax is -1. So if you just set rax to 0 and let it run, then it will say, "Are you daddy?" So it's kind of like how I envision we can kind of change the behavior of whatever is running inside this sandbox from the outside. Okay, that's it for the demo. So thank you a lot. I do have a Discord that you can join if you go to codetracer.com. I'm also on R2's Discord and Telegram. So if you are interested in kind of contributing or helping out with this project in any way, let me know. And enjoy the conference. Thank you.
Any question? We have some minutes. Oh, have a question.
Are you fully rebooting the VM every time you do a new run?
Well, I experimented a little bit with this. So as I told you, in last year, first I kind of decided to rewrite the front end because I wasn't quite happy, and then I decided to rewrite the back end. So before, in the old back end, we used to always require you to have a snapshot that you will revert back to.
Yeah, that was what I was thinking.
And then I was experimenting a little bit with this. For now, I kind of want to have both available because it saves me a lot of logistical challenges if I don't have to keep like a huge tree of like big snapshots. So for now, but you don't need to, but you can. So in the first demo, I run it multiple times, but that's just without actually reverting it. So obviously, if you have some type of malware or something, it can screw up the system, and then you might want to revert. But it's also really much faster if you don't require the user to always revert back to a snapshot. So I just haven't gotten around to having snapshot support so far.
Thank you.
Thanks.
Any other question? No? Thank you. Big applause.
Thank you.
pancake.
Please, 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 have a seat, have a seat. Have a seat. Esta noche, carricoche. Hostia, que eso está grabado, tío. Ay, no bella. Julián, Julián, por favor. Alex, are you ready? So, we are now ready for Hitchhikers Guide for Unity. Unity, yeah. Reversing iOS games by Alex. Big applause for him.
Hello, can you hear me? So last talk, I know that you are super tired and maybe sleepy, so I will try to make it funnier as possible. The idea I will to show you my journey about trying to reverse engineer some iOS games, just for fun. Like, okay, you know, when you are just playing and just maybe frustrated, and it's like, okay, what can I do if I just reverse engineer the game, and what is the possibility to just bypass some feature and just create new features for you and have even more fun with the game. So that was my idea. First of all, who I am. My name is Alex. I'm known as Murphy as well. I'm a mobile researcher at Now Secure, yet another one. And I'm an R2 evangelist as well. I like it a lot. It's just a tool that actually I'm going to use it in some demos. That's the idea, just to combine R2 and the Frida world all together, and you will see how powerful it is. And that's my handler for almost everything, so you can find me just using that. That's the first thing. That's a big disclaimer, like, okay, I'm just going to teach you how to reverse engineer iOS games, but I don't want to create cheaters. Actually, we have some anti-cheaters around you, so be careful. That's our agenda. The idea is just to talk about a little bit Unity. How many of you have you coded some game on Unity? Just raise your hand. Okay, sweet. And in mobile? If you don't know, mostly all of the games in App Store, I said mostly, not all of them, of course, are coded using Unity. And if you don't know exactly what it is, that's what I'm going to show you right now. Actually, Unity is just cross-platform development. That's why it's so powerful. That's why it's so used across the community, not only for iOS, it's used as well for Android and for Windows. And the idea behind it just because you code only one application, it's code on C#, and then when it's cross-compiled, with the same code, you are able to run exactly the same game on Android, on iOS, even on Windows. That's why it's so powerful. That's why it's so used. But I'm going to show you why as well. What is the caveats of using that kind of platforms as well? How is the build process working on iOS? How is? So it's just Unity. When you code the C#, it's compiled to an intermediate language. That it's something derived from C#. I think it's proprietary for Unity, just something specific for it. And the idea then is just to compile it to C#, to C++, sorry. And this is compiled inside a library. Actually, for iOS, you can find this inside a framework that is called Unity Framework. And here it's where all the interesting part is found. Actually, this is the resume of what I already said. The idea is just you have the C# source code, there's a C# compiler, then it's creating some DLLs, then it's using some bytecode stripper, that is something internal for Unity, and with the stripper assembly, it's like, okay, this is not even used, so I'm just going to use that part. I'm using IL to CPP, that is just some automatic process that is getting the intermediate language to C++. And then that C++ code is just compiled to create the application itself, and all the result is just here. So if you open one Unity application, that it's the IPA, it's just the format that iOS used to distribute applications. In the end, it's just only a zip file. So you can just unzip the IPA. You're going to see all the files inside. And the important part is just the library. So you're going to find the main binary, that is the main binary for the application. But this binary doesn't have anything. So just have wrapper functions just to make the translation between the Objective-C wall or Swift wall to the code that you did, and it's inside the library itself. So this is how it looks like if you open an IPA, and then inside a folder that is called frameworks, you will find the framework itself, and this is exactly the piece of code that you are interested on. You need another piece, and it's because the cross-compiling process requires some metadata to do some reflection, or just it's something internal for Unity. And this metadata, it's even inside the IPA. Usually, you should be able to find it inside a file that it's called global metadata.dat, as you can see here. And this metadata is actually the function names, the arguments, the parameters, the return values. So it's like the information itself of what a method is actually doing. So quite useful if you're doing a reverse engineering process, because this is giving you a lot of information that you can use on your process. Some of games, unfortunately, they obfuscate it because they know how powerful is that information, so they are just trying to obfuscate it, or they encrypt it, so that's the plan. But this information should be there. So it's just a matter of time that you should be able to get this information. So here, for example, I'm using r2frida. That is just calling some Frida APIs to get the modules and the files and the maps created in memory. And if you look for the global metadata, and actually here what I'm doing is just listing all the memory maps, filter with the tilde for global metadata, it's the file name, and then I'm just filtering as well for the read-only sections. And just with that, I'm able to get where this file is found. And actually, if I xdump here 32 bytes to that direction, you should be able to see that content. So actually, this is a magic number that is always the same for this file. And if you, for some reasons, you are not able to find it, because maybe they just changed the name, that there are some games that are doing that kind of stuff, the only thing that you have to do is just look for the magic number in memory, and you should be able to get the map. And if you just dumped the content of memory to a file, you should be able to see exactly the same as the original one. So once we have this information, we have the Unity framework with all the code, we have the game binary as well, and as well, we have the global metadata. So only with these two pieces of information, and here I'm using one tool that is well known. When you are just looking for some information about reverse engineering on Unity, this is one of the most used tools for do this process. This is just making the pieces together just to create the DLLs, some decompilation, and some files with information that it's including the ILC2PP headers and all this metadata processed in a JSON file. So the idea is just to use this file that it's called script.json, and inside this file, it's where you should be able to see all the information that you need to reverse engineering, because there we should be able to find the name of the method, the arguments, the return value, and as well the address where you should be able to find the code that it's implementing that function. So there you go. We have it everything. So this is an example of how it looks like. It's just, as you see, the name, the signature, just the return values, and I mean, just with that, you have most of the work already done for you. So what am I going to do with this information? Okay, we have the Unity framework. We have the script.json. So we have the Unity framework that is the code, but it's stripped. So if you check it just with R2 with the command I, and we get information, we can see that it's stripped. So we don't have symbols, we don't have information, only on the binary. However, we have another file with all the information. Why not just put it together and see what happens? So here I'm using this script. It's already published. It's in the R2 GitHub. And this file is just a JavaScript file. It's pretty stupid if you see the code, and this code is thanks to Pancake as well. But the only thing it's doing is just processing the script.json file, getting the names, getting the addresses, and it's creating flags that is just marking all the methods inside the binary. So if you remember, we had the stripped binary, and just processing this information, we should be able to see this is the code. I'm just going to zoom in this method. So actually here, you have some idea of what it's doing without doing nothing. And actually here, you have how I use the script. That it's just a matter of opening the Unity framework, just run the script as a JSON file, and R2 have a JavaScript engine that is processing this internally, and there you go. You have all the flags inside the binary itself. Okay, thanks Pancake for the spoiler. But yeah, I'm using AI, as Pancake already showed. The idea is just, instead of explaining what is the R2 AI, what is the Kai, we are going to see a real example and a very useful use case where you should use, or you can use, just what Pancake showed this morning. So the first thing is just, with R2 AI, you should be able to communicate with different AI models, local or remotely, like Cloud, OpenAI, or whatever. And it's super easy to install. I'm actually using R2PM just to install it. But in the end, what I'm using is just the Kai. That is just, it's just a collaborative way to communicate between models. The main goal is just to enable some contributions from others just to train all together one model. But thanks to Pancake, we have a plugin just to communicate with all the different models that we have in internet or local, and getting all the input from the R2 session and just put it on the model itself. So how to configure it? Super easy, at least for me. It's because I'm just changing the API. I'm just using the one from Anthropic that it's called Cloud. And then I'm just using the lang. If you remember, Unity, it's code in C#. So I just want the result in C#. So once this is configured, the only thing that I have to do is just, okay, I'm just moving to the method itself, run the Kai-D, and that's all. And here you have some examples of real games, what you can get. So here, once everything is symbolicated with the script I previously mentioned, you can just decompile one method, and you have here, you know that this method, for example, just reading a little bit, you know actually what it's doing. So if you should be able to interact with this method, and you have a game that is using gems for whatever, you can get free gems just interacting with this method. Or if you have a game that you're unable to run on a jailbroken device, by some reason it's like, okay, I don't know what's happening. Okay, maybe this method it's called, there's some interesting Here, this is from another game, and you have exactly the checks, and it's almost super close to the original code that it's actually running. Okay, it's time for playing with the games. What I'm going to use? I'm going to use r2frida. I think you have heard a lot of r2frida, but no one's presented, right? So r2frida is just a tool. It's open source. It's inside this repo. And it's interacting. It's getting R2 session, and it's using the powerfulness of Frida just to interact all together on the same place. So the idea is that, for me, at least, the most important part, especially for this talk, are the two latest features that are involved. That it just, I'm able to read memory. I'm able to disassemble the application in memory, and I'm able to modify the application in memory. So the idea is just, okay, I can use R2 as it should be a local file, but in the end, I'm just playing in memory. So if I crash the game, I can just restart it, and I can continue playing with it. And I can even call in methods. So I can just identify a function, that, like, for example, the addGems function, and I can just use r2frida to call this function. And actually, if you remember, you know exactly the arguments expected by the function. So it's super straightforward. Like, OK, if it is expected a pointer, I just create a pointer with the expected output, and there you go. So time for demo. I'm praying for the demo gods. And I expect to be like this at the end. So the first thing is, can we improve the game experience? I'm not saying cheating, OK? Let's see what we can do. So usually when you are playing with this kind of games, they are expecting some special inputs when you're calling methods or whatever. One example is like, OK, I just want to call a method that is implemented in a controller, but this method is an instance method, so I need actually a reference to that controller. How it's possible to get this reference? So maybe there are a lot of ways to do it, but this is the one I found that for me was easier. That it's like, OK, I'm just going to hook the method that it's called pause, and just put a breakpoint, and then I'm just going to get the reference, just getting the x0 value. So this is like actually a real pointer in memory that it's pointing to the game controller instance that then once I get it, actually I can use it for whatever I want. So let's see how it goes. So this is the script, the JSON file. Here we have the pause method. Just going to, and I'm just going to plop, run a game. OK? This is the way to use r2frida to attach to a process. I'm just using USB, and this is actually the process name, that it's a random game. So then what we need, the first thing we need is just a reference to the Unity framework, because we are actually using the Unity framework, but we need to rebase all the addresses with where it's been loaded. So I'm just going to filter out Unity, and so this is filtering the output, and I'm just filtering for the Unity framework, just getting the map with read and execution permissions. So actually, I'm just going to put this inside a flag, just to remember it and avoid to have it to run it again and again and again. And then I'm just going to get the post method, just getting the address, and get the base address plus that value. So actually, this is the method that is implementing that method. So I'm just going to create a breakpoint. All the r2 frida commands, if you see, are preceded by a colon at the beginning. So that's the difference between the r2 wall and the frida wall. So I'm just going to put a breakpoint and resume the game, pause it, boom. I have the breakpoint hit. So I'm just going to list all the registers, and with the dot at the end, it's just to list all the registers of the current thread. Just going to get it, and if you remember, the interested one is just x0 that I'm not able to see. There you go. And actually, I'm just going to put it in a flag. I'm lazy. So actually, if you see, the game is frozen. So it's waiting for someone just to resume the process. So if I click DC, just continuing. So the breakpoint, it's not hit it anymore. So I'm just going to remove the breakpoint just to avoid being noisy. And we are going to see what we should be able to do with the game controller. So I don't know if you know the game, that is a temple run, that is just a guy running. So I found a method that is called boost player. What is going to happen? I don't know. Let's try it. So let me just look in here, boost player. There you go. So actually, these are the arguments expected by the method. It's just the game controller itself. If you remember, I already got it. It's just looking for a distance and a bool and another pointer that actually you can ignore. So something that we can do is just, OK, I'm just moving to the method. This is a R2 instance. This is statically. This is just the Unity framework already symbolicated, opened, and emulated, just to get all the reference calculated. And then here you have all the code. And this is actually the boost player. That is the same method I was looking for. I'm just going to use the Kai, because I don't want to read the disassembly, and see what's the result. So just to try to understand what is the method doing under the hood. So the internet is quite slow, so just be patient. As you can see, be patient. There you go. So here you have, in real time, a decompilation of the function itself. You have the arguments. This is just the game controller. And it's funny, because the distance method, that it should be that one, anyone is able to find where it's used? It's not even used. So why I have to be worried about this parameter if it's not even used? So actually, we only need the argument 1. That is what we are going to use. So let's continue just getting the reference to the boost player. If you remember, I have to rebase it again. I'm just getting the pointer. Here, and just putting the game just to see that I'm not cheating. Okay, you can see the guy there, just running out of monkeys. And now I'm just going to call this method, but if you remember, I'm just going to use the game controller. But this is just the game controller I saved inside the flag. This is just the hack that I used to use exactly the same value. And if I resume the game, phew. So actually, it's just a matter of, okay, I can play all the time I want. All right, this is fun. We know exactly how to do this, but it's not enough. As you see, I died, so it's just pressing all the time. I'm lazy, remember, so I just want to play without even touching anything if it's possible. Let's continue. There are some obstacles on the game that you're going to crash. Why not just avoiding them by default? So here, the way I use it's quite different. I'm not just calling a method. The only thing is just, I'm just getting the method that is handling the obstacles, and then just overwriting the beginning. If you remember, I can disassemble the method, and I can even modify the instructions inside the method. Why not just return and do nothing? Let's see what happens. So let's look for game controller, handler, how was the name? Handler collisions. It's just right here. So I'm just going to move to the method and just run PD5 just to disassemble the method. You can see some instructions here. And what I'm going to do is just write a return instruction. If I disassemble again, oh, sorry, you have the instruction here. So actually, right now, every time that the game is just trying to handle a collision, what's going to happen? Let's see. So okay, I'm just going to swipe. This is a tutorial because I had to reinstall the. That's the AI. It's only the word for another one. But it's not enough. As you remember, you can die. Why, if I just get the method that is handling the end of the game and just do nothing? And as well, I found another method that is it's called resurrect. It's like, okay, I can play all my life the same game and never ends. That's super good because I can just leave the game and continue tomorrow, the same game. Sorry. Okay. I'm super bad with memory, so let's see. Game controller, handle, and game. Actually, here I'm just combining the two different strategies. Like, okay, I'm just adding the return value just to do nothing, and then I'm just going to call a method just to do some specific stuff from the game. So let's just calculate this stuff again, move it. This is actually the method that it's not this. It's not this one, right? Thank you. And the idea is just to repeat exactly the same process. So we are just going to return. And then just look for the other method that it's called game controller, resurrect, There you go. I'm just going to prepare the command. Sorry if I'm slow, I need another coffee. So right now, I'm just going to resume the game. Okay. Just going to die. Boom. Okay, this is because it's a tutorial. Just let me finish it. It's super funny. Huh? You can see. Not really. Yeah, it's because the tutorial is like, okay. Now it's just going to start. Okay. Now it's like frozen. Just going to click. Boom. I can play again. So right now you can play all your life if you want. But it's not enough. So in games, okay, that means that I have to play. So, okay, now I can play all my life, it's not ending, but why if I can just get extra coins? So instead of just getting one value per each coin, why not just multiplying per 100, 1,000, or whatever? Here, actually, the only thing I'm doing is just, okay, I'm just getting the method that it's called add coins. I'm just doing a decompilation of the method. I see that at the beginning, if you can see that it's in purple, at the beginning, it's just doing some check. Like, okay, if the value is less than 1, just return and do nothing. So I'm just going to remove this condition, and I'm just going to add it. I add a move, like, okay, instead of 1 coin, just put the value that you want. So, okay, this method is different. So this is the method. I'm just getting the value of the method. Just going to reverse it again. As you can see, it's quite straightforward once you get exactly how to do the stuff. Just going to move to the method. Here you have the 2 instructions that I mentioned. So why not just, I'm just doing the comma because I'm going to write some main instructions on this memory position. So I'm just going to write move 100, I think it's fine. I'm just going to write a knob just to avoid the branch. As you can see the result here, you have the move and the knob on top. I have to resurrect it again. And just check the coins, that it's just the value. So now it's easier. Yeah, why not? Yeah. So, this is actually what we did. It's just, as you see, that's how r2frida is powerful. It's just, you can disassemble in memory, you can see the instructions, and if you know exactly what you're doing, you can modify the instructions and do whatever you want. But it's not enough. because this requires to analyze one game. But I'm lazy, remember. What if I can get, why if I want to get resources from all the games only with one shot? That's possible? So if you know what is an in-app purchase, it's just a process that all the games, or mostly of the games are having, that it's like, okay, the game is free, but if you want to get adding gems or just extra coins, you have to pay. And it's like, okay, just pay €1 for, I don't know, 100 coins. And I said, okay, yeah, it's fine, but I'm not rich. So this is the process, actually, that it's involved when you are doing a purchase. That in the end, it's like, okay, this is the game. It's just making a request to the App Store. Then you get the pop-up like, hey, do you want to pay I don't know, €100 per this purchase? And you say yes. And then the game is just validating the transaction with the game server. The game server says yes. That guy that is checking the stuff with the App Store is saying yes. That guy paid €100 for this transaction, so just give him all the coins he asked. And it's like, okay. But do you think that all the games are doing that server-side checking? Let's see. The answer is no, obviously. So actually, it's like, okay, they are just making the request to the App Store, and then it's just waiting for some response like, hey, the purchase has been done, and the game is like, it's just happy and says, okay, thank you. Give you the coins. So this is an example of a decompilation of a game, just to see that if the purchase is correct, it's just depending on the type of the purchase, it's just disabling the ads, giving the gems, or give infinity pack. But it's doing nothing. I mean, it's not validating nothing. So what could go wrong? So here I have another game. Boom. This is what it's an in-app purchase. Let's buy some stuff. That's making just a request to the App Store. It's slower because the internet here it's kind of creepy. But there you go. No. Well, I can pay. Let me check. So I'm just going to run a Frida script. This is actually Frida. It's a Frida JavaScript. And actually, I'm using R2Frida with this, with the dot at the beginning, just to load the Frida script and use it inside that session. So actually, what the Frida script does is just pretending that the purchase has been done successfully. And it's just modifying some stuff. It's quite slow. But yeah, I mean, it's worth. It's $3. That's a good thing. Okay, from 5 demos, just failing 1. It's fine, right? There you go. So, finger crossed. Anyone has $3 to lend me? I'm just going to cancel the purchase. Boop. Boom. So, wrapping up. We learned how to reverse engineer Unity games. We know exactly how to use the metadata from the games itself and make some fun. The important part is just the feature. I mean, this is something that I did on my free time as well. But there are some games that are doing better, the stuff, like protecting the metadata, obfuscating it. There is some literature in internet related to how to get it. There are some tools that they are not open source, so it's like, or you use it or just forget it. My idea is just to implement all this stuff, if it's possible, using R2. Like, okay, I'm just going to try to get how to decrypt it, how to defuscate it, and even I'm just working on trying to get rid of the IL2CPP dumper, because it's a tool that it's mainly used on Windows. I don't like Windows, so it's like, okay, I don't want to use it anymore. Unfortunately, it's open source, so I'm able to get the logic and implement it on R2 side. So actually, I'm working on just creating a script to do it everything with R2 if possible. That's the plan. So that's it. Thank you.
Any question, cheaters? I'm afraid right now of these guys. Edu?
Remember the disclaimer.
Well, thank you for the talk. I have one question. It's about the AI. So how was the compilation of Swift before the AI? I mean, it has been improving a lot, or it was different?
So now it's of Swift?
Yeah, Swift.
So instead of C#, using Swift, you mean?
No, instead of using the AI, how was the compilation before? I mean, it was similar. It has improved. I mean, I don't do much iOS.
I don't know. Yeah, it's like, okay, just getting the compilation using PDC, then put it on Cloud, and it's like, okay, just rewriting with the variables names that it's getting and the method name that it's getting as well from the metadata, and it's just trying to make, as he said,
it was not as clear as it is now, right? It was not that clear.
So actually, if you use IL2CPP dumper, you're getting the compilation, but sometimes, I mean, you're getting something like, okay, the method is doing something like this, but it's like an idea. And sometimes the compilation is not complete, and sometimes as well, you don't have the compilation itself. It's like it looks like the method is empty, but in the end it's not. So the code is there. So that's why I don't like that tool, because for me it was incomplete in terms of, okay, once, if the compilation is empty, what should I do? I don't know. Like with this method, I'm able, once I get it working on an application, as you see, it's just a terms of have fun, because you can do whatever you want on the game.
And another question is, have you reached the #1 in the scoreboard? I mean.
Fortunately, I closed the application before uploading the score. But yeah, you can do it.
Yeah, one question here. I saw that you extracted all these symbols from the metadata and then imported those. How common is that you find all the symbols shipped with the apps? Because I suspect that games shouldn't be shipping the symbols with the package application.
This is a thing from Unity. So by some reason, I don't know exactly why. Maybe it's some reflection or whatever, but I think it's the price you have to pay to have one code working for all the platforms.
But can they strip that from the distributed package?
From what I've seen, nope.
Okay. Yeah.
So I've seen obfuscation. I've seen.
Yeah, but I guess obfuscation
encryption,
pre-building.
last question is the global metadata that file contains actually types, structs, and also.
And yeah, not a question, but I just pushed a commit that it's updating the script to add the base address, so you don't need to add it all the time.
So I don't think we'll find any other conference in the world that during the talk someone is like pushing to the repo to fix shit. Okay, that's good. That's good. I was near to him like, what the fuck are you doing? No, I'm fixing that. I was like, during the talk. Okay, thank you very much.
Thank you, Pancake.
Any other questions or PR? Okay, thank you, Alex. Thank you very much. Woo. Sí, bien. Sí, déjalo para hacer ahora. Barnat. Hello, hello, hello. Thank you to stay until the end. This is the final talk. It will be like a 3 hours workshop from Sergi. Thank you for being here until the end, and Sergi will do the final words for the conference, so room is yours.
Thank you. Can we get my screen in the big projector? Perfect. So yeah, don't worry, it's not a workshop. So this is the closing keynote. So I would like to thank everybody for coming. I thought that you had some good time here. You learned a lot of stuff. You had fun with other people. We had some nice food and drinks, some practical workshops, nice memorable presentations, and yeah, and finally we had some meetups after the conference, having some beers outside and having fun together. Yeah. What's next? Because maybe there will be a conference next year. I don't know if that will happen and when will happen. Actually, the date that we choose for this conference was not the one that was the common date for r2con. It was supposed to be happening at the beginning of September. But yeah, we decided to pick a different one. It was working best for all of us. And at the end, there was many other things that we missed in this event. So there was like R2 Wars, CTF, maybe we can organize more trainings or longest ones because there was not enough time in 2 hours for practicing all the stuff that we learned. Maybe we can improve the logistics. So yeah, the plan is to send you a form to respond. And so if you can have and spend 5 minutes giving us some feedback anonymously, we just care about learning from you. We want to know if the schedule and the timings was good or not. If one of you are interested in some specific topics or you missed any specific talk or training, we'd love to know that. So yeah, depending on the feedback again and the mood that we get, I think that we will end up deciding to make it again next year, or maybe not. That's a mystery. So, but yeah, anyway, whatever happens, just stay tuned and check the Mastodon account or Twitter or so on, and the chats, and we will be announcing some news sooner or later. Yeah, stay connected. Keep not just the social networks, also the code network. We keep pushing pull request contributions and discuss whatever you like and contribute to the project. And yeah, finally, it's not over. So this is not the last day of the conference. Tomorrow there will be more presentations, but don't worry. You don't have to come here. You don't have to get up earlier. Just open YouTube and we'll be posting the videos of the remaining presentations. That's basically, there was some people that was not able to make it for different reasons, but they were looking for presenting the stuff that they were doing with Radare. So there is a bunch of presentations, and also after that, we plan to publish the videos edited from the current day and also the trainings from yesterday. So if you missed anything or you want to review or check another presentation again, we'll be pushing everything online as soon as possible. So yeah, that's the end. But before finishing, I would like to say thanks to all the organizers, all the people that was helping on organizing the event, looking for the venue, looking for the food and checking everything, helping all the speakers, doing the schedule and everything. So please, I would like you to come here. A big applause. And thank you. And I think that Seyfried have some words to close the event.
let's go and push some PRs to the repo and let's contribute all together. See you next year, guys.